list forms. After that, we so introduce some topics in week 5. So there is one topic, shortest path, and there is one topic, spanning tree, and there are different types of algorithm to perform these different uh, problems. Okay, so we will start from the shortest path problems. Yeah, so first algorithm is the Digestive algorithm. So Digestive algorithm is basically used to find the shortest path from any given source to any other all other source, all other vertex. Okay, so the Digestive algorithm return the shortest path from any given source to all other vertex in the graph. Okay, so some properties are there for the Digestive algorithm. So Digestive algorithm works for both directed and undirected graph. So we can use this Digestive algorithm to find the shortest path for both type of graph, directed and undirected graph. And Digestive algorithm doesn't work for a graph with negative weight or negative weight cycles. Okay, so doesn't work means it may be represent the correct output, or it may not be represent the correct output. So for negative weight cycles, and what is the negative weights means here? So we can understand the what is the meaning of the negative weight cycle and negative weights. So both type of graphs, for example, if we have a graph, so I'm representing the directed graph and undirected graph. So for example, we have a graph A, B, C. Okay, so we have a edge like this. So 10, 25. So so in this graph, directed graph, so all weights are positive. So there is no problem with the positive weights. If graph have positive weights, so we can apply the Digestive algorithms. But what happens if any weight is negative? Okay, so for example, if we are taking that here weight is -2, we are talking about the undirected graph now. So what is the meaning of negative weight cycle in directed graph and undirected graph? So in undirected graph, if any negative weight is given, so for example, if we are at here and we are moving to D, C to D. Okay, so C to D, we will what is the negative weight is -2. So we can reach at the D in -2 with the -2 weight, but we can also move from D to C also. Okay, so D to C, if we are moving, then so this weight, this value, for example, initially this we are starting from C, and the weight for the C is 0, and we are moving from C to D in -2. Then we can also move D to C, so it become a, so now it become -2, -2 plus -2 -4. So now it will so this value of the shortest path will become less. So initially it was 0. Now we are getting the negative value -4, which is less than the 0. So we will update again. Then if we once again move to the D. Okay, so we are starting from -4, then -4 plus -2, then it become -6. So it is also less than to this one. So we will update this. So in undirected graph, if any negative weight is given on any edge, so that is considered as a negative weight cycles. Okay, so for for Digestive algorithm, so we, if negative weight is given on any edge, so it considered as a negative weight cycle. So and for the directed graph, so for example, if we have a directed graph A, B, C, D. Okay, so for example, if we have a directed edge, like this. Okay, so we have a weight here now, for example, 20 -10 and 5 and 3 and 6. Okay, so can you tell me this graph have a negative weight cycle or not? Can anyone tell me?
So
Yeah, Braj. Yes, Braj.
I think so. There isn't any negative weight cycle. Like if
Yeah.
the
So
complete.
yeah. So in the directed graph, if for example, if we are starting from the zero, this A node, so we can move to B in 20. So 20. Then we can move from B to D. 20 minus 10. So now it becomes 10. Now we can move to the D to A. 10 plus 5, 15. So initially it was the 0, now we are getting 15. So the value is increasing, not decreasing. In if graph have any, if graph have any cycle and graph contain the negative weight on any edge, if we are moving through the cycle, so the value of the initial node should not be decreased. So we are starting from the 0, after traversing on the cycle, so we are getting the positive value. We are not getting the less value from the initial value. So that means this graph not have a negative bit cycle. So for example, if represent that minus 15 here, okay. So it represents that the graph have negative cycle. So for example, if we are starting from the 0, then we are moving to the bit by 20. So 20 minus 10, 10, 10 minus 15, then we are getting minus 5. So it is less than the 0. So this initial node value will be updated once again. So it become 5. Then we will start, we will repeat this cycle. So it value will again reduce. Okay, so this is called the negative weight cycle for a directed graph. But in undirected graph, so if any edge have negative weights, that considered as a negative weight cycle, because we can move in the both direction. But in the directed graph, we can move according to the given direction. So this is called the negative weight cycle. And what is the difference between negative weight and the negative weight cycle in the graph? Okay, so we are moving to the back on digestive algorithm. So now digestive algorithm doesn't work for graph with negative weight for or negative weight cycle. Okay, so this is clear. Uh, this algorithm returns the shortest distance from the source to all other nodes, but after some modification like maintaining parent information of each node, we can find out the shortest path. So initially in algorithm, generally we used to find out the shortest distance value only. But after some modification, we can use any dictionary type of data structure. So if we maintain the information of parent node for each node visiting, so we can find out the shortest path also. So for example, we have a graph. So okay, I'm just taking an example how we can solve using the graph this problem using the digestive algorithm once. Okay. Okay, so we have a graph and we are interested to find out the shortest path for all node starting from the 0, and how we can find out the shortest path using digestive algorithm. So how digestive algorithm works actually. So initially, so graph, for example, we are starting from this is the source node, and we are finding out the shortest path value for every node. So initially we will assign the 0 weight for the source node and infinite value for the others node. Okay. So this is the first step, initialization step in digestive algorithm. This is I am representing that. So after that we will select the node with the minimum distance. So minimum distance node is 0. Now this node will be selected, and we will update the distance of the neighbors node. If the neighbors node distance is less than the previous distance, so we will update it. So if we are starting from the 0, so 0 we will check that what are the adjacent of 0 is 1 and 2. And if we are moving from 0 to 1, so what are the distance is 10, and 10 value is less than the infinite. Okay, so we will update this value 10. So it become a 10. Now second adjacent is 2, So we can move from 0 to 2 by 80, this 80, and it is also less than the infinite. So this become a 80. Okay, so this is the first step. After updating this, we mark as this is visited. In algorithm, we will never look this node again. Okay, if we are marking that this node is visited, so we will never look this node again. So once again we will select the minimum distance node. So which one of the node is the minimum distance node? So now 10, 80, all others are remaining are infinite. So we will select this 10, this one, because this have a minimum distance. So we will select this one, and what are the adjacent of this one is 4 and 2. So for updating the distance for 4 and 2, we will add the previous distance, because we are finding out the shortest path from the 0 node. So 0 to 1 is 10, which is already contained by the node distance. So this is 10. We will add the value of 10 into the next distance. So 10 plus 20. So this is 30. Now previous distance is infinite, so 30 is less than infinite. Now it become a 30. Okay, same for the next node. So 10, we are here, and we can move to the 2. So we can move from 1 to 2 in the 6. So what are the previous distances? 10, 10 plus 6 is 16, and 16 is less than the 18. So we will update this, so it become a 16. Okay, so now this node is visited. Okay, so now we have visited node in 0 and 1. Now once again we move to the next node. So which one have the minimum distance? And now this 16 have the minimum distance in the remaining unvisited node. So we will select it, 2. Now 2 we can move only to the third node. So now if 16 plus 70, 16 plus 70 is 86. So 86 is less than infinite, so we will update this 86. Okay, there is no adjacent remaining for the 2. Now we mark as the visited node. And which node will be selected for the next third, this 30 node. Okay, now remaining is 86 and infinite. So now this 4 will be selected, and we will if we find out the distance for the neighbors, 4, so 30 plus 50, now it become 80, and 80 is less than infinite, so we will update this 80. And after that we can move also 4 to 6. So we can 30 plus 5, 35, so it become a 35. Okay, now 4 is visited. Now we have remaining 5, 3 and 6. So which distance is the less minimum? This 35. Okay, so we will select this 6 node now. Okay, so 6, now we cannot move from anywhere from the 6. So there is no update will be happen by the node 36, 6. And now we will select the next minimum node. So next minimum node is this 80. Okay, so 80 we will select 5, and from 5, so we have a 80 distance from the source node, and if we add this 80 plus 10, this is 90, but 90 is not less than 35. Okay, so we will not update this. Now it remain the same, and now it is also visited, this is visited, and it is also now remaining one node is remaining 86. So we select it, we cannot move anywhere from 3 node, there is no neighbors for that, and now there will be no change. So finally these last updated value represent the shortest path from the source node. If we check that 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5, 0 to 6. So it represents the 10, it represents 16, it represents 30, and 0 to 4 is, so 0 to 3 is 86, sorry. 86, 0 to 4 is 30, and 0 to 5 is 80, and 0 to 6 is 35. Okay, so this is the shortest path value. Tanuja sir, PA question 4 in digestive algorithm. Could you please explain that to practitioner question number 4? Okay. Okay, so you can find out that how we are calculating the digester shortest path using the digester algorithm. Okay, now we will check that. So this is the just information for the shortest path value. What happened? So for how we can calculate, how we can find out the path for any node. Okay, so for example, if we are we will maintain a dictionary parent. And okay, so initially we there is no. So initially we will initialize as a 0, none. Okay, 1, none. 2, none. 3, none. 4, none. 5, none. Total 6 node and 6, none. Okay, so we are starting from the 0, so it value remain the none because there is no parent before. And for the second time, so for example, if when we are selecting the next minimum weight, okay, so we can store the parent value in our dictionary. Okay, so for example, so if we are maintaining that, what are the next updated, if we are selecting the if we are updating the weights from the 0, so this 10 value is updated by this 0. Okay, and this 80 value is updated by node this 0. So at the first process, or first we can say the first pass, when we update the weight, if any time we get the new weight which is less than the previous weight, so we will update that the new weight we are getting from the which node. So this initially it was the infinite, so we are getting 10, so we are getting 10 from the 0 nodes, so we will update this 0 node. Okay, for the first. And I'm just representing into the next term. So initially it was none. So for the 2, we are initially it was the infinite, and we are getting 80 from the 0. So we will update this information 0 here. Okay. So same for the second. Then we are selecting this one node. After this one node, we can move to the this 4 and 2. So for 4, we are getting 30. Initially, it was the infinite. So we are updating the weight because we are getting the less weight. So we will contain the information for 4. We are getting 30 from one node. So this one is the parent for the node. So we will update this here 1. Okay. So same for the is this 2. Now we are getting 10 plus 16, which is less than the 80. So we are also updating the weight at this time, but now this time we are getting this 16 from 1. Okay, so this was previously updated by 0, but now we will next updated this by now 1. Okay, so same now we will select the next 16 weight. So we are updating the weight of the third. Now this is 86, and we are getting this 86 from 2. We are assigned that this is the parent of this 3 is 2. Same for if we are after that we will select this 4, this node 4, and we can move to the 5 and 6. So we are updating this 5 weight, and this is 80, and we are getting this 80 from 4. So we will update the parent 4 here. And same for the 6, we are getting this 30 plus 5, 35, and initially it was the infinite. So we are updating this weight. So we will contain the information. We are also getting this from 4. Okay. Now we will select the next smaller node. So this is 6. There is no updation happened from this node. Now we will select the 80. So this so from 5 we are also not updating the weight for any neighbors node, and then this 86, and there is no neighbors for that. So finally we get the parent information for each node. Okay, this is the final one. So we can find out the path. So for example, if we are interested to what are the path for 0 to 6. Okay, so 0 to 6 path we will start from the previous node. We will check the parent node of 6. So what is the parent? We will start from like this. We will check that what is the parent of 6. This is 4. Okay, now we will check what are the parent of 4 is. This is 1. and what are the parent of 1 is, this is 0. Okay, so this in the reverse way we can find out the shortest path for any node. So we can, for example, if we are interested what is the path for the 4, so we are starting from the 4 and check the parent node is this is 1, and what is the parent node of 1 is 0. We will repeat this process until we will find the parent as source node. Okay, so this is the parent information we can find out by the just containing the information of parent node when we are updating the weight. So one question someone asked for the PPA.
Yes, sir. Week 5 PPA 4, sir.
Yeah, PPA 4. PPA or PA? PA 4. Okay.
Sorry, package assignment. Sorry.
Okay.
PA 4.
Yeah, so this is the same concept. This algorithm is given, and this comment is also condition for update the distance from the source. So same things, we will contain the information for every node like in that way. So when we are updating the weight, so if we are getting the less weight from the previous weight, we will contain the parent information for that node. Okay, so in that way, so we will find out the path. We can find out the path by in the traversing in the reverse order. So the question is the similar to this. Consider the graph above. There are multiple shortest paths from S to T in the graph. Which of the following path will be considered as the shortest path by the given algorithm? So same things we do. Which process I have mentioned for the another example. We can apply the process on that this example. So this is a graph. Just I think this is big graph. Just a wait, I'm copying this graph. So 5. So this is the given graph. Same thing, we will start from the S node. Now it is 0 and another are the infinite. Okay. So we will start from the 0. So if we are selecting this S, we can update the weight for B. This is now it become a 3, it become a 4, it become a 7. So these weight are updated at the same time. We will contain the information of parent node. So what is the, so now I'm writing that. So S, A, B, C, D, E, E, after the E, G, T, E, F, G, T. Okay. So this is the null, and we are the updating the weight A, B, and D. So what is the parent of A now? So A parent of 0, and B is 0, and D is 0. Okay, after the first updation. So now
parent is S.
Sorry. So parent is S. Okay, so now we will select the minimum distance weight now. So now we have 7, 3, 4. Okay, so we will select B, and after selecting B, so we are getting this 3. So 3 plus 4, 7. Okay, so algorithm is given in the question. So algorithm says that when we are updating the wait, this is, yeah. So this is less than. Okay, so no. Okay. If distance is plus, yeah, it is, if it is less than, then we are updating. Okay, so this is not less than. Yeah. So in the previous distance is 7, and we are also getting the 7, so we will not update the weight, and also not update the parent information from here. So same things now. There's no change now. It is visited. It is visited. Now we'll select the next smallest node is, this is 4, and this is now A. From A we can move to the C, and for C the weight will be updated. It become a 5. 4 plus 1, 5. Now what are the parent of C is A, so it is A. Okay, now A is visited. Now we will select the next smallest. So now 7 and 5, we have 2 nodes with the minimum distance. So we will select C, and from C we can move to the D by 5 plus 2, 7. So which have already 7. We will not update this, and we can move to the E by 5 plus 1 is 6. So it becoming 6, and what will be the parent of E is C. Okay, so same things. Now after that we will select the next. So who is the next?
D.
No, this is 7 and this is 6. Yes, 6. So we will select E. So from E, we can move to the G, we can move to the T. Okay, so
Sir,
from,
shouldn't you first do D though?
no, because this have weight 7 and E have 6. So we will select the minimum distance. Okay.
Okay.
Yes, so we will select E. Now from E we can move to the G. Now 6 plus 2 is, it become a 8. Okay, and from E to T, so 6 plus 10 is 6 plus 4 is 10. It will update it. So we will contain the information for this. So G we are we are updating the weight, and we are updating from the E. So for G it become E, and it is also E. Okay, now E have visited. So we have already C visited, E visited. Now we will select the node. Minimum distance is 7, 8, and 10, and infinite. So we will select D. Okay, so 7, 7 we can move to the, from the D we can move 7 plus 1, 8 to E, but it have 6 only, so we will not update it. We will we can move 7 plus 3 to T. Now 7 plus 3 is 10, so it is also similar, so we will not update this. And 7 plus 5 for F, so 7 for 5 is 12. Now it will update. Okay, so there is only one weight is updated now, so we will update for the F parent. So we are getting the from the D here. Okay, and now it is visited. We will select the next smallest. So the next smallest is this 8, and from 8 we can move only we can move to the E back, but in digestive algorithm we will never visit the visited node again. So we can move we can visit only this T. Okay, because T is not visited now. So 8 plus 3 is 11. So previous is 10. So we will not update it. So now there is no change. Now we will select next. Now this is 10. From 10 to T to F, 10 plus 5 is 15, but previous is 12. So there is no updated. And after selecting this F, there is no update. So finally we are getting the parent information, this one, and we are finding out the parent node. So we can find out from the T. We will start from the T. From T, what is the parent is E, and for E, what is the parent of E is G. No, EC, sorry. What is the parent of C? Okay. And what is the parent of C is?
A.
Yeah, A. And what the parent of A is? S. S. This path will be written by the digestive algorithm. So S is ET.
Sir, but this is not the shortest, na sir?
Why it is not sorted? What are the weight? Total weight is
Sir,
total weight.
SDT has the same weight 10,
Yeah.
but it is
How you are measuring that the shortest path? Shortest path represented by the distance, total distance. Now distance is 10.
sir, but it has the minimum number of nodes, na sir?
No, so why are you
If you take
thinking about this?
SDT,
No. So why are you consider this for the shortest path here? Number of vertex.
no sir,
It was
both
in
are shortest one because both is 10, but I am talking about the least number of
Yeah, so
nodes.
digestive algorithm not consider this for the least number of vertices or anything. It return the shortest path according to the total distance, not the number of vertices. For number of vertices, if
So
all
both
weights
the
are,
part,
yeah,
sir, both the all three paths SDT and from SB,
yeah,
both are same. All the three paths are the shortest path, right, sir?
yeah. So in these things is given in the problem statement. There are many possible paths. So there are multiple shortest paths from S to T. These things is given in the problem statement, but asking that which of the following path will be considered as the shortest path by the given digestive function.
Okay, sir, got it.
Okay, so for example, if all weights have the same weights, okay, so in that case, all weight have the same weight. In that case, we can use the BFS algorithm, and the BFS returns the shortest path in terms of the number of edges. Okay, so we can apply the BFS algorithm to find the shortest path in terms of the number of edges in between. Okay, so now this is the topic. Yeah. So digestive algorithm never look back if a node is visited, so it will never look. So because of that, for the negative weights. So for example, if any node is visited, so it will never look before because we are marking that node is visited. So in the given so for example, if any weight, any edge is given like this, okay. So now weight is say 16. Okay. So now this is now 80. Now this is not correct. So for example, to make one cycle. So one, we are updating this from 2. Now this weight is given from here, and this is minus 12 minus 12 6 8. Now we can take any 6. So this is 10 plus 6 16 16 minus, for example, 7. Okay. Yeah. So for example, in this graph, there is a one back is given from 2 to 1 with the weight of minus 7. So if we are starting from the 0, so the first node will be selected as a 0. Now second node will be selected as 1. Now we will move this 2 node will be selected. Now there is negative is as given as with the minus 7 weight. Okay, so this because one have already selected, already visited, so we will not check this for the negative weight. Okay, so we will not check this uh, reverse edge where we can receive the minimum weight for the one. Okay, so for two, now the weight, total weight is distance is 16, and we can move to from the 2, 16 minus 7, so we will get the 9. Okay, so but digestive algorithm did not check the visited vertex again. So because of that, for negative weight, it will not work. So the algorithm is given for the code is given for the both code. Now we are moving to the Bellman-Ford algorithm. So Bellman-Ford algorithms work for the both directed and undirected graph with non-negative weights. So here this terms is given for non-negative, that means the positive weights. So for directed and undirected graph, so I have already explained that the for undirected graph, if any negative weight is given on any edge, so it can consider as a negative weight cycle. So because of that, the first statement is written there in the form. Works for both directed and undirected graph with non-negative edge weights. Bellman-Ford does not work with an undirected graph with negative edge weight, as it will be declared as a negative weight cycle. So same statement is given here. So Bellman-Ford works for a directed graph with negative edge weight, but not with negative weight cycles. So it works for the negative edge weight, but not for the negative edge weight cycle. So here example is given.
Yes, this means that Brilliant 4 doesn't work for cycles.
Negative weight cycle. Hello.
Only negative or just, I mean, it can be.
Yeah. So can you see this graph?
Yes, sir.
Yeah. So if you are checking from the sixth node, okay. So there are two negative weights are given on the edge. This is a directed graph. Okay. So there are two negative weights are given, but there's no cycle is forming for these edges. So you can if you are at 6, you can move to the 5 with -5. So it for example, so you can move to the 5. So if you are adding the side, so there is no
Just a
cycle actually.
second.
Hmm?
Sir, in the fifth node, so
Hmm.
there is a cycle 1 to 5, 5 to 2, and 2 to 1, and having a negative weight also.
So can you repeat the which node have a cycle? 5,
The
1, 2.
5,
Okay,
1,
yeah.
2.
Yeah.
oh,
So which have a cycle. So for example, we are starting from the 0. We are starting from the 1. Okay, and we are adding this one. So 0 value to 2. So 0 plus 2 is 5, and you can just explain the graph. Okay, yeah, the graph is given here. Okay, so if you for example, this is the value 0. If you are adding this 0 to 2, okay, so it become a 2. Now 2 minus 2 is 0, and 0 plus 1 is 1. So after circulating on the side, after moving on the cycle, so for initial state, you are not getting the less value from the initial value. Okay, so initial was 0. After moving to the this cycle, you are getting 1. So this is not a negative weight cycle.
Okay, sir.
Okay, if you are getting the less value from this 0 after moving to this cycle, you buy this negative value. So that represents the negative weight cycle.
So in case at the place of 1 there would be -1, it won't work.
Yes, then it will not work, because we can move, we can repeat this cycle again and again, and we will get the less value every time.
Okay.
Okay.
Hmm.
So message is given. Yes. Okay. So for this type of case, for this is the graph. There are some negative weight is given, but there is no negative weight cycle. in this graph. Okay, so if you see any cycle, so there is no negative weight cycle. So for that type of graph, we can use the Bellman-Ford algorithms, and Bellman-Ford algorithm also represent the shortest path from the any given source node to another node, Okay, so same things we are started. So we will repeat this process. Total number of vertex. So how many number of vertex are? So 1, 2, 3, 4, 5, 6, 7, 8. Okay. We will repeat the process 8 times. So we will take one loop for this number of vertex, and every time we check that what so initially we will store that, so this is 0 initially, all this is infinite. So same things like a digestive algorithm, we will initialize that, and after that we updated the vertex if overall weight is 0. Yeah, so it is also not affect the so it is also not considered as a negative weight sign. So negative weight means, so we are reducing the weight from the initial value, that affect the distance. Okay. So
Sir,
for
so
the
zero cycle is also allowed.
sorry.
So for positive cycles and zero cycle also it will work.
So you are
Only for
saying that,
negative cycle.
yeah, negative weight cycle. So actually negative weight cycle creates a problem. So if we
There
are
is
starting from 0 and then we are getting 0, so there is no effect for the weights. We are getting the same value for the initial value. If we are reducing the value of the initial value, then it will create the problem, because we for example, we are starting from 0. Okay, so now we are getting -2 after moving this cycles. For example, if we are considering that this is the -1. Okay, so we are starting from the 0, 0 to 2, 2 minus 2 this, or we are also representing this is -2. So we are getting -2. Now we are starting from the -2 now. So -2 and 2, 0, 0 minus 2 -2. Now -2 -2 -4. It become -4. Then it will increase continuously in that. Okay, so because of that, the negative weight cycle creates a problem, and we get the less value of the initial value. So for the first loop we will take a one loop for so there are total 8 nodes, so we will start from 0 to 7. So for 0 value we will check that from the first node. Okay, so we will start from the first node and check that what are the adjacent of that node is. So 0 you can move to this 1 and 7. Okay, so this value is less than the previous value, so now it becomes 10 and it become a 8. Okay, after the first okay, now we will so for the second so we will consider as a, we will check for the all nodes now. Okay, so for the this 0 value we will check for all. For example, we will check for 0, 1, 2, 3, 4, 5, 6 and 7. What are the adjacent of this 0 is 1 and 7. Okay, so 1 and 7, we will update the weight for that. Now we will check for the 1, what are the adjacent of 1 is. So here we are not selecting the we are not finding the vertex using this minimum weight formula we are using, which we are using in the digestive algorithm. So we will repeat this process for every vertex. So here so for example we will check for the 1 now. So now from 1, so we have received this 10 value from the 0. So we can move from this 1, so we can move to 5, only 5. Okay, so we will add this distance also because we are finding the shortest path from 0. So 10 plus 2, now we are getting 12, so which is less than the previous value. So we will update this 12. Okay, so now it is updated. So 1 week and 5. So now we will check for the 2. So what are the adjacent of 2? So adjacent of 2 is, this is the infinite. Okay, so the value of the 2 is infinite, and we are checking for the 2 nodes. So what are the adjacent of 2 is 3 and 1. Okay, so we will check for the both sides. So infinite plus 1 is infinite, and infinite is not less than 10, so we will not update this. So now this is 1 and 3, and we will not update any weight from the 2 nodes. So it will also not update it 3. Okay, so infinite plus 1 and infinite, so both are the same, so we will not update it. Now we will check for the 3. So what are the adjacent of 3 now? So the adjacent of 3 is 4. So in the weight is infinite, infinite plus 3 is also infinite, so this will not update it. Okay, same for the 4. Now 4, what is 4? This is 4. So we can move to this infinite value to 5. So infinite minus 5 is also infinite, and previous value is 12. So we will so 4 adjacent is 5, but we will not update this. Okay, so for same for the 5. So we have the 12 weight at 5, and we can move to this 2, only 2. Okay, so this is minus 2 now. Okay, so minus 2, 12 minus 2 is 10. Now previous is infinite, so it become a 10. So for 5 we are updating the 2, and now we will check for the 6. So 6 is infinite, so there will be no changes for the if the distance for node is infinite. Okay, so there is no change. So this is 1, this is 5. Okay, we can move to the 1 and 5 from the 6. Now 7 have 8, and we can move to the 6. So 8 plus 1 is 9, so which is less than the previous value, so it become a 9. Okay, so after first iteration, so we are updating these value for the graph. Okay, so this is for the 0 only. Now we will repeat process again for the 1. This is for 0, now for 1. So same things we will check for once again. 6, 7. Okay, once again we are starting from the 0, then when check, so the initial value is 0, so we can move to the 0 to 10. Now previous value is also 10, not updated, so 1 and 7. So 7, so it is previous 8, no change. Same for the 1. So now 1, now value is 10, and we can move to this 5. So 10 plus 2 is, this is 12. Okay, so we can move only 5, there is no change. And for 2 to 1 to 3, 1 and 3. So from 2, 1 and 3, so this is 10, and we can move 1. Okay, so 10 plus 1 is 11, which is greater than 10, and 10 plus 3, 10 plus 1 is 11 for 3. So now it will update it now. Okay, so it becoming 11 for this case. Okay, so say same for the 4. Now this is 3. So for 3, now it have updated, so we can also update it the adjacent weight. So 11 plus 3 is 14. Now it becomes change 14. Okay, 4. Now for the 4 value is 5, so we will check the 4, 5. So we can move to the 5. So the negative weight is considered. So this is 14 minus 1 is 13, but 13 is greater than 12, so we will not update this. We will check 5, 2. So we can move to the 2. Now 12 minus 2, this is 10, not updated. Now 6, for 6 we will check for the 5. Okay, so we can move here. So 9 plus 1 also. Okay, 9 minus 1, 8. So previous value is 12, so this will it become 8. And we will check for the 7 now. 7 is 8, 8 plus 1 is 9. Okay, so same process we will repeat total number of times, 8 times, because it have a 8 vertices. So after repeating this process 8 times, we will get the shortest path value for each node. Okay, so in this case, we are checking the every vertex. If it has already visited, so we are also we will check again in the next process. Okay, so here if negative weight is given for if negative weight is given and negative weight cycle is not found, so it will check the this reverse back edge for finding out the shortest path. Okay, so Bellman Ford working in that way. So it returned the shortest path from given source to all other vertex. So this is the second algorithm for this type of category. We call that this category single source shortest path. Okay. Now next category is all pair shortest path. All pair of shortest path. Okay. So in the previous single source shortest path means we are taking a one source. Now here we are considering that we are finding out the shortest path for every pair of the graph. So if we are interested, we are checking the shortest path, for example, in this graph. So if we are finding out that what are the shortest path from this 1 to 2, so it will return. If we are checking that what are the shortest path from 7 to 2, so it should be written by this algorithm. So basically, if we apply the finding the all pair shortest path using digestive algorithm, so we have to apply a digestive algorithm for on every node as a source node. So once we apply the digestive algorithm on this 0, then 7, then 6, then 4, so we can find out this information all pair shortest path. But using Floyd-Warshall algorithms, so we can find out the all pair shortest path using one algorithm. So find the shortest path between every pair of vertices I and j. It is equivalent to it is equivalent to if run digestive algorithm or Bellman Ford for each vertex from each vertex as a source. So these are some properties. So Floyd-Warshall works for both directed and directed graph for non-negative edge. And okay, so for negative, if negative is given in the undirected graph, so consider as a negative weight cycle. Floyd-Warshall algorithm is an alternative way to compute transitive closure. Okay, so we can also using this algorithm to compute the transitive closure. So you have already seen this algorithm, transitive closure, where we find out the reachability from every node. Floyd-Warshall works for a directed graph with negative edge weights, but not with the negative weight cycles. And this is the basic formula to update the distance in our matrix. Okay. So this SP represent as a matrix. So for example, if we take this small graph, so there are lots of computation happen by this algorithm. So we cannot take big graph. Okay, so for this graph, for example, okay, so first matrix we created that like for example SP 0. So we are starting. So SP -1 we are considering that this is the initial matrix. Okay, so we will directly create it using a graph. So this is the just representation of the graph. 0 1 2 3 4 0 1 2 3 4. Okay, so we just check that is there any. So there is no edge from 0 to 0, 0 to 1, yes, 10. This is the positive, this is the undirected graph, or they all it are positive. Okay, so I'm just representing that. So 10, now 0 to 2 is no, infinite, 0 to 3 is 18, 0 to 4 is infinite. So there is no direct edge, then we are representing as an infinite value. And for the same edge, we are representing as 0. So 1 from 1 now. So 1 to 0 is 10, 1 to 1 0, 1 to 2 20, 1 to 3 6, and 1 to 4 infinite. So 2 to 1, 2 to 1 is 20, 2 to 0, 2 to 0 is infinite, 2 to 1 is 20, and this is 0. 2 to 3 is infinite. 2 to 4 is 8. Okay, so same with 3 to 0. So 3 to 0 is 18. 3 to 1 is 6. 3 to 2 is infinite. And 3 to 3 is 0. 3 to 4 is 70. To the 4. So 4 to 0 is infinite. 4 to 1 is infinite. 4 to 2 is 8. 4 to 3 is 70. And 4 to 4 is 0. So this is the initial matrix. So this is we are considering this is the graph matrix we have already. So now we will calculate the shortest path using this given matrix. So we will start from SP0. So this 0 represent that the k value actually. So we will check the so for ij. So okay, so we will calculate the every position value. So we have an initial matrix 0 1 2 3 4 and same for the 0 1 2 3 4. So this row represent as a I and column represent as a j. Okay, so we will fill every this position value. So this is this position is represented by the combination of I and j. Okay, so we will apply this formula. So s of I comma j, we will fill. So this is the k matrix. So k value will be 0. Okay, so k matrix. So k is 0, and we will select min. What are the distance between I to j directly in the previous matrix? So we will check the previous matrix value. So we have this matrix, previous matrix, updated matrix. So we will check what are the value of sp k minus 1 for I to j. Okay, this represents the direct distance if there is no direct path is available, or we will check the path through this k node. So if we are considering that is 0, so we will check that we will move to the I to j via this 0 node. Okay, so we will check the path for this matrix in that way. So this second formula is sp k minus 1, and the value will be I to k and plus sp k minus 1 and k to j. Okay, which is smaller? So we will update the value in this new matrix. Okay, so for example, we are calculating this position value. So I 0, j 0, and k is 0 for all complete matrix. Okay, so we will apply this formula and fill all the value in this matrix using this formula. Then in the next process, we will calculate the sp1 matrix. Okay, so sp1 matrix, same formula we will use. Now k become 1. Okay, so we will check the direct path from I to j and check the path from I to 1 and then 1 to j. So which is the shortest? Okay, now we will fill this sp1 matrix using this formula. Now k value is 1. Same for the sp2, we will fill. So for filling the sp1 one value, we will check the value in this formula by in the previous updated matrix. So for this sp1 matrix, we will read this value. So we will read this value from the previous matrix k minus 1. Okay, so we are taking 1. So k minus 1 is the 0. Now we will read the value from the previous matrix from this for sp1. For sp2, we will read the value from this sp1. Okay, so we will sp3 and sp4. Okay, so there are 5 nodes 0 1 2 3 4. So we will calculate these 5 matrix. So this is the initial matrix. Now we will calculate this 5 1 2 3 4 5. Every time we will look the value from the previous matrix and fill the value using this formula. So when we are getting this final matrix sp4, that will represent the shortest path from every pair. Okay, so this formula is representing in that way. So we cannot calculate every single value in this time. So it will take lots of time. So total 5 nodes is given. Now 5 into 5. Okay, so 5 into 5, 25 for each matrix, and 25 into 5, 125 times we have to apply this formula to calculate every single value. So algorithms work like in that way. So this is the basic formula for the Flood-Warshall algorithm. Now next topic is
Sir,
yeah, yes.
sir, I want to I have one doubt, like how to detect negative cycles using Flood-Warshall algorithm.
Okay. So because we know that we are filling this zero value for every I to I combination. Okay.
Yeah.
Okay. So after completing this process, if we get this negative value, because if we are starting from here, okay, so so we are feeling that the zero value, and is there any negative cycle, so we are moving from like that way, and this is the -10, this is 18, and this is -16. So after moving in that way, so we will get the negative distance which is less than to this zero. Okay, so we will update this information in our matrix. So after completion of this process, we will check that the value of for every I to I combination. Okay, so 0 to 0, 1 to 1, 2 to 2, 3 to 3, and 4 to 4. So you will check this position value. If its value is decreases as a negative value, so we can say that the graph have a negative side. Okay, just check what is the SP. So this is the last matrix, SP4 I to I value. Okay, so you are checking the I equal to 0 to 4. Check for the all.
Yeah,
Okay,
sir.
so
Okay. If it is less than 0, then there is a negative cycle.
if it is less than 0, then it represents that it is negative itself. Okay, now next topic is spanning tree. So spanning tree is basically as a name suggests, the tree. So tree represented as a there is no cycle in the graph, and every vertex is connected. So graph is remain as a connected graph, and there is no cycle in the graph. Okay, so non-negative transitive closure. Siddhant, transitive closure is similar to this. Okay, I will take after this spanning tree. Okay. So spanning tree, basically we are converting a graph into a tree form. So tree have some property. So there is no cycle in the should not be in the tree, and the S should be one less than the total number of vertex. Okay, so this form will represent as a tree. Retain a minimal set of edges so that graph remains connected. So graph remains connected after removing the edges. So recall that a minimal connected graph as a tree, adding an edge to a tree create a loop. So after creating a spanning tree, if we are adding any edge, so it should be created a cycle in our tree. Removing an edge disconnect the graph. So after creating a spanning tree, so if you are removing any edge, so it become a disconnected graph. So want a tree that connected all the vertices. So this is spanning tree definition. So more than one spanning tree in general. So here term is used spanning tree. So there are many possibility to create a spanning. So there are more than one possible spanning tree possible for any graph. But what is the minimum cost spanning tree? So minimum cost spanning tree represent the total cost of the edges should be minimum in our spanning tree. So that spanning tree is called the minimum spanning tree. So for example, if we are creating a, so we have a graph, for example, A, B, C, and D. Okay, so we have a edge like that. Okay, so for this graph we can create a many spanning tree. Okay, so if for example we can remove this edge, So we have a one spanning tree. So we are considering also that 1, 3, 4, 2. So after removing this 2, this is B, this is C, this is D. Okay. Now it represents as a spanning tree ST1, and we can also represent another spanning tree. So we, for example, if we are removing another edge, so B is T, and this is C. Okay, so this is 1, this is 3, this is 4. Same for the 1, this is 2, this is 4. Okay, so there are many possible spanning tree can be created. So what we are interested to find out the minimum cost spanning tree. So what are the cost of this spanning tree is 1 plus 3 plus 4. This is 8. This is 1 plus 2 plus 4. So this is 7. So in that way, so we can create many spanning trees. So we will find out the minimum cost spanning tree. So total edge weight should be minimum. So for example, in this tree, so if we create a spanning tree like this A, B, and C and D. Okay, so this is 2, this is 3, this is 1. Now it return is 6. So this is the minimum cost, total minimum cost of the spanning tree, and you cannot create a spanning tree less than this cost for this graph. Okay, so this spanning tree is called the minimum cost spanning because it have a minimum cost, total cost of the edges. So this is the minimum cost spanning tree. Now we have two algorithms to find out the minimum cost spanning tree. One is Prim's algorithm and second is the Kruskal algorithm. So how Prim's algorithms works? So Prim's algorithm, it is also similar to the digestive algorithms. So we will take the, yeah. Okay. So for example, if we have a graph and we are finding out the what are the minimum spanning tree for this graph. Okay. So we can start from any node. In minimum spanning tree, we can start from the any node. And after selecting, so for example, if we are starting from the 0, so we will mention that this is the distance 0, infinite. So I am applying the Prim's algorithm here. Okay. So when we start from any node, so if you are starting from the one node, so you initialize the distance for one is 0 and remaining for infinite for remaining. So now we will select 0 and we will check that what are the adjacent edge is connected. So there is two edge connected, 10 and 18. Okay. So for we will update this by this 10 value and we will update this by this 18 value. Okay. And which is the less? Okay. So which is the less value? Oh, one sec. Okay. Now. So this information is updated. We will not select the edge now, and after that, when we will select the minimum weight node. So what are the minimum weight node is 10, and where from we are getting this 10 value 0. So we will consider that this 0 in our tree. Okay, so I'm just representing this node here. 4, 5, 6 and 3. Okay, I'm not adding any edge. So we are selecting the node 1. So we have already selected. Now we are selecting the next minimum weight node. This is 1, and this weight 10 value we are getting from the 0. So we will consider this edge as a spanning tree edge in our final result. Okay, so now this node edge is selected. Now we will update the distance for adjacent node. Okay, so same for we will never look the visited node again. So 0 have already visited. Now we will not look this weight again. So we will now we are at 1. So we will update the 4 distance as 2. Now this time we will not consider the previous edge like as the digestive algorithm. So we will update the distance like in that way 10 plus 20 and 10 plus 6. But here we will update the distance only by this edge. So we are at 1. So from 1 we can move to this 4 by 20. Okay, and for 2 we can move 6, and which is less than 18, so we will update by this 6. Okay, so at this time, so now this node is we have already selected, and now age we have marked. Now the what are the next weight which have the minimum? This time this is 6. Okay, now this 6 weight is updated from the one node, so we will select this 6 this edge in our spanning tree. Okay, so 6, this is the 10. Okay, now we will check the adjacent of for the 2. So now this is 2 to 3 is 70, so it will update to 70. Okay, now we have already selected 2, and so all other nodes are visited, so there is no update happening. So now what are the another node remaining? Now 20, 70, infinite, infinite. So we will select this 4, and this 20 value updated from this one node. Okay, so we will consider this edge as a spanning tree edge, this 20. Okay, so now from the 4 we will update the next adjacent weight. So from 4, this 5 is we will update this value 10. Okay, so 4 to 5 is 10, and 4 to 6 is 10 also. Okay, so same things. Now 4 have selected. Now we will select the next smallest weight. Now we can so here 10 and 10, two weights have the same weight, so we can select any of them. So if we are selecting 5, okay, so where from we are getting this 10 value? From 4. So this value will be this edge will be selected. Okay, and we are if we are updating that, so what are the edge from 5 to 6 is 5. Okay, so which is less than 10, so we will update this 5. Okay, so there is no remaining. Okay, so now we will select the minimum. So now 70 is remaining, 5 is remaining. So we will select the node 6, and this 5 is we are getting from this 5, so this edge will be selected. So now this 5 will be selected, and there is no update from the 6 node. Now one node is remaining, this 70. Okay, so from this 70 we are getting from this node 2. Okay, so we will select this 70. Okay, so in that way we can create a we can find out the minimum spanning. So this is the minimum spanning tree for this graph. Okay, so what are the minimum cost for the spanning tree is? So you can add all the weights. So 10, 6, 20, 10, 70, and 5. You can add all these values, that will call the total cost of minimum spanning tree. So that is the minimum cost. So in that way, you can apply the Prim's algorithm. And second algorithm is the Kruskal algorithm. So where first we consider we will select we find out the spanning tree using the edge information. Okay, so first we maintain a record for the edge, and sorting the edge according to their weights in increasing order. Okay, so how many edges are there? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 edges is there. So we will just write the edge in the sorting order. So which one is the smallest? So this 5, 6 is 5, and this 1, 2 is 6. 1, 2, now next is, so there are many 10. So 0, 1 is 10, and 4, 5 is 10, and 4, 6 is 10. Now next one is this 18. So 0 to 2 is 18, and 1 to 4 is 20, and now 2 to 3 is 70. Okay, so we first we will sort the all edges in increasing order of their weights. So after that we will consider the edge one by one. So we are just starting from, we are consider that the every node as a different components. So this is 0, this is 1, this is 2, this is 4, 5, and 6, and this 3. Okay, so we are considered every nodes are is a different component. So this is not a connected in any way. So we will just consider that we will just take the edge one by one and check that if it is created, if it create the cycle, then we did not consider that as. If it is not created the cycle, then we consider that our spanning tree. So 5, 6. So for 5, 6, it is not created the cycle, then we directly add this 5. Then 1, 2, 1, 2 is not created the cycle. Yes. 0, 1. This is 0. So 0, 1. This is 10. Oh yes. Okay. Not created any cycle. 4, 5. So 4, 5. This is also not created any cycle. So 10. Now 4, 6. So 4, 6. Yeah, if we are consider the 4, 6 edge in our spanning tree, so it creates a cycle. So we will not consider this 4, 6 edge. Now 0 to 2. 0, 2 is 18. So 0, 2 is 18. Yeah. So if we are marking this edge in our spanning tree, it creates a cycle. Okay. So we will not consider that. Now 1, 4. So 1, 4. Yeah, it not create any cycle. So we will consider that 20. And 2, 3. So 2, 3 is also okay. So it creates. So if you see the both, so both are the same. Okay. So both algorithm return the same minimum cost spanning tree, same minimum cost. Okay, but it can return the different spanning tree. For example, if there are many bits, so for example, if we are considering that, so if we are just taking this edge before this 0, 1, okay, so this will select first 4, 6. Okay, so if graph have edge with the similar weights, so there are a possibility to create different minimum spanning tree using Kruskal algorithm. Okay, as well as the Prim's algorithm, because here if you are seeing that, so we selected the 10 and 10. So if we are selecting the next vertex, minimum vertex as a 5, so spanning tree will create the different, and then if we select the 6, then it will create in the different forms. So but the total cost of the spanning tree will remain the same. Okay, so there are more than one possible minimum spanning tree using these algorithms, but the cost of the minimum spanning tree will remain the same. So using this, how we can check that the cycle is creating or not? So we use some union find data structure or some concept. Find using this we can find this cycle is creating or not in NES. So if you can find it this in algorithm. So this is Prem, this is Kruskal. Yeah. So this is the component things where we maintain a parent node information for every components. So if anytime we are creating a edge, we are adding a edge, so we just maintain this information who is the parent, one parent. Okay, so every connected components we can maintain a one node as a parent. Okay, as in this component information. So using this, we can find out that this edge is created cycle or not in the given spanning tree. Okay, so if you apply the one example using this algorithm, you can find out that how we are checking that the cycle is created or not. So, so this condition is tested that cycle is created or not. Okay. Yes, yeah. So Prim's algorithm, you can start from any node. So all will return the same answer. So transitive closure. Okay, let's find out that where is this topic. Week 5. In any one assignment, I think this topic is given. This. Yeah. So this definition is given for the transitive closure if there is at least one path between vertex I to j. Okay, so we will represent as a one value. If path is available for any combination, so we are checking that 1 to 3 path is available. Yes, available. So 1 to 2, 2 to 3. So we'll mark as the one. Okay, so if you see this matrix, so now answer is this one. So here we are just checking for the all combination. So here row is 0, 1, 2, 3 and column is 0, 1, 3, 1, 2, 3. So if path is available from any starting node to any destination node, so then we are representing that one. So transitive closure basically represent the reachability from any node to another nodes. Okay, so I think one problem is also given in the one of the assignments. So using this, you can find out the and this matrix. One of the practice assignment, I think. Okay, like what is long? Yeah, so this problem is given. So if you see the solution, yeah, this is the simple solution for the transitive closure. So it is similar to like a float Warshall algorithm where we are taking these 3 loops, and after that we are just checking that the condition using this. So here actually we are using this 1 and 0 combination. So we are filling this matrix in that if Sij equal to 0. Yes. Okay, just see the solution for this practice assignment and just check the solution, and we'll take this. We have 3 weeks remaining actually. Okay, any query from week 5? Okay, we are moving to the week 6 now. Yeah, so first topic is union find data structure. So actually we are improving our classical algorithm using this union find data structure. So we are just creating this union find data structure, and yeah, this is the algorithm of improved algorithm using union find data structure. So here actually we are just we are containing the information for every vertex in our dictionary components. So this contain the parent node basically of any connected components. This is the represent the members who are the member of component, and this represent the size of our members. Okay, so using this information, these are 2 functions where we are just creating a union and find. So this is the base. This is the initial function, and these are 2 operations we are actually using in our classical algorithm: find and union. Okay, so in find function, we are just returning the who is the parent node of the we are considering the edge in our spanning tree. So for example, uv is the edge, so we will check the component of the for the both u and v. If the all component value is the same for the u and v, so that means it creates a cycle in our spanning tree, and we will not consider that. So if you can see the classical algorithms, so here, yeah, this condition is given for every edge We are just checking that the if a component of u is not equal to the component of v. So if this value is equal, that it represents the as duv as is created the cycle in spanning. So we will not consider that. If it is not equal, then we will apply this union process. So basically, this union method update the our component information. So component, member, and size information after adding this new edge in our spanning tree. So duv, we are adding this edge in our spanning tree. So we will update all the information for the components. So actually, we are reducing the operation time for the Kruskal algorithm using this union find data structure. So this is the coding part basically, and priority queue. So now for the before the priority queue, so now we come at the heap concept. Heap, yeah. So heap, for understand to heap, before just understand what is the binary tree basically. So binary tree is a tree data structure in which each node can contain at most 2 children. Okay, so binary, the name is represented binary as a 2 value, 0 and 1. So same things we are considering in the tree. So we can take maximum only 2 childs. Okay, so any node can have 0 child, 1 child, and maximum 2 child. Okay, so that type of tree is called the binary tree. And we represented this child in the form of left child and the right child. Okay, so when we draw this binary tree, so we will consider this one child in the left side and second child in the right side. So this type of form is called the binary tree forms. So heap, basically what is the heap? So heap is a binary tree and it is a complete binary tree. Okay, so it is a complete binary tree. That means every label should be filled before the last label, and in the last label every node should be filled before the last child. Every child should be filled before the last child. So if you see this diagram, so you can see that every label, so there are 4 levels in this tree is given. So one level is h0, second level is h1 and h2, and third level is this h3, h4, h5, h6, and fourth level is this. So before this, the last level, every level should be filled. There is no missing child should be there. Okay, so and in the last level, this is the h9 is the last child. Okay, so before that, every child should be filled. So okay, so this type of tree is called a complete binary tree. So heap basically is a binary tree or complete binary tree, and we can represent this heap tree structure using the list. Okay, so if we traverse this heap complete binary tree, or we consider this heap in the label order fashion. So label order fashion means we will start from the root and read the value from the root and left to right terms. Okay, so we will start from h0, then we will move to the next level and start from the left child to the right child. Okay, so h0, h1, h2, then next level h3, h4, h5, h6, and h7, h8, h9. In that way, we can represent this heap in our list structure. Okay, so here the heap form is given as a tree, and this tree is also represented as a list form. So h0, h1, h2, h3, h4, h5, h6 in that way. Okay, so but how we can find out which one is the child of which node and which one is the parent of any node? So for this information, we can just using this formula, we can find the parent and child information using this formula. So for example, if we are finding the left child of hi, so I is represented the index of any node. So for example, if we are finding out this who is the parent of this h4, okay, so what are the index of this h4 is 0, 1, 2, 3, 4, okay, so we can find out the left child. So just we will multiply 2 into this 4 value. 2 into 4 is 8, and 8 plus 1 is 9. So 9th index is the left child of that node. So 4, 5, 6, 7, 8, 9. H9 is the left child of that one. Okay, same for
Sir,
the right. Yeah,
sir, one question here, like, do predecessor and parent mean the same?
sorry, can you repeat once again?
Do predecessor and the parent mean the same?
First word I'm not getting. Parent or
Predecessor.
Predecessor.
predecessor. Oh, predecessor. Uh, so predecessor is depend in which sense you are considering this predecessor value. Sometimes we just consider that the based on the value based predecessor. So which is the predecessor value? Sometimes we can say that in the level order predecessor. So level order predecessor is H9 is 886, H8.
So the value one.
So according to the value, we cannot say that predecessor. So predecessor, for example, if we are traversing this tree in order fashion, okay. So there is some terms used in the who is the in order predecessor. Okay, so in that case, predecessor represent another things, different things. For example, so if we have a tree like that, so for example 10 and binary search 5 or 1 8 12 and 18. So if we just represent the in order traverse. No, so your voice is breaking. We are not getting. Who is this? Okay. So this predecessor terms in representing the different forms. So if we are, for example, we are representing the traversal. So 1, 5, 8, and 10, 12, 15, and 18. It represents the in order traversal. Okay. For this tree. So sometimes we are asked that what are the in order predecessor and what are the in order successor for any, for example, 12. Okay, so who is the in order predecessor for 12? So in order predecessor for 12 is 10. Okay, who is the in order successor for this 12? This is 15. Now in that case, this is not the parent. So 10 is not the parent of 12. Okay, so predecessor and the successor just represent in a specific way, in specific terms.
Basically, previous and next value.
Yeah. So in binary search case, so for example, in deletion of any node, so we just, for example, if we are deleting this 10, so we are just checking that who is the in order successor of this 10. So this is the in order successor, and who is the in order predecessor? Now this is the in order predecessor. So we swap the value, then delete this blue child. So
Actually,
yeah,
here there was a question like previous terms quiz too about
do you
this.
have a question?
Yeah, but I don't know how to tell it to you because there is like a tree here, big tree.
Quiz 2 previous term question. Huh?
Yeah,
1 second. Yeah,
it's the third question.
1 second. I think some is.
Sir, the tree was a balanced search tree, sir, in the quiz question.
Actually, if you have exact questions, you can send in the chat box, or otherwise I'm searching that. Okay, wait for. So quiz 2 question. This set. This question here.
Sir, in any set you can find, sir. In one set it was predecessor, in another set it was successor.
Okay, just wait. Yeah. Just choose the choices.
In that question, we have to find in order, and then we have to see the one which is
Yeah.
above
Okay.
that.
Yeah, okay. I'm just copying the question. One sec.
Okay, sir.
There's one question. This is
Yeah.
yeah. So here some information is what is the predecessor in terms of the value. Okay. So in terms of the value means this is the binary search tree actually. Okay. So predecessor means which is the next, which is the just before value. For example, our element is so same for this in terms of the value. So we are also say that this is the in order traversal. In order traversal. So in order traversal, actually the value are written in the sorted form for the binary search tree. Okay, so in the previous question which I have written, so for example, if we have a this tree, so 15, 10, so 20, 12.
So if nothing is given, we assume it's in order transversal, right?
So no,
Traversal.
if anytime we are asking for the pre-order and success, predecessor and successor, definitely it will the supported information will be given. Otherwise, anyone can think about the parent info. Parent is the predecessor. So here value is given is the in terms of the value. So for this terms of the value represent the in order traversal actually.
Okay.
5 and for example this is 16.
Instead of 12, can you write 16?
Yeah, I'm just changing that. Yeah, so 16.
So, sir, if I'm not wrong, but by value you mean that M is in the right branch of the C's subtree. So that means M is greater than C, and that like in turn means that C was uh, lesser than M,
No, so
kind of
just
thing.
compare this diagram to this diagram. Okay, so this is the binary search tree, and this is also a binary search tree. Okay, if you are asking that who is the predecessor of 20, so we will check that in the we can manually check this information. So who is the just before value? Before means just the if we are written these value in the sorted order. So 5, 10, 12, 15 and 16 and 20 and 25. Okay, so which is the closest less value of this 20, which is 16?
Yeah.
That is predecessor in terms of the value. So here we are just representing this in order traversal. Actually, in order traversal represent the shortest form of the binary search tree. If you are traverse this tree in order fashion, so it return the shortest list. So it predecessor just represent the closest less smallest value from any node, and successor represent that the closest upper value of any given node. So if you are asking that who is the closest of for 10, so 10 who is the successor, who is the successor of 10, so the closest value of 10 which is greater than 10, this is 12. Okay, so in you can see in the 12 is coming just after this 10 in
Sir,
order
how would you
traversal.
do this for this? What like you would write A
For
B C
this,
D E F G?
no, so just traverse the tree in order fashion.
Okay.
Okay, just apply the in order traversal for the
What is
given
the
graph.
predecessor of 16?
Predecessor of 16 is 15. This is 25. Is someone saying Instead of okay. Okay, so for this question, you have to just write the in order traversal for the tree. So in order traversal for this tree will be H. Okay, H D. Then O I and P, then B, then J E K, then A, then L, then F, then C, then M, and then G, then N. This is the in order traversal. Okay, we are finding out who is the predecessor of this M. So we'll check that who is the predecessor of this M is C. So answer is C. Okay.
Okay, sir. Yeah, yeah.
Okay.
Sir, instead of 16, if it was 14, then the predecessor would be 10, right?
So no. So instead of 16, so 14 cannot come in on the right side now, because 14 is less than 15, so it cannot come at this place. Well, this is a binary search tree according on the
Okay, so to maintain in order, we have to be like it should be greater than 15.
yes. So in this is the property of binary search tree actually. So every value of the right subtree should be greater than this 15. Okay, and every value of the left subtree should be less than this 15. This rule will be applied on every node
Okay,
in binary search tree.
got it, sir.
Okay. Okay.
Got it. In every level, it should.
Yeah. So this rule will be applied on every subtree part. Okay, you can apply this rule on this 20 value. So the right subtree part is 25, which is greater than this 20. Okay, and the left subtree of this 20 is less than this 20. So we will apply this rule on every part. So okay, we are just taking the binary search example now after this topic. So yeah, this is the binary heap representation, and we can find out the left child, who is the left child, right child, and who is the parent using these formula. Okay, so actually we are just representing in the tree form to understand the heap concept, but in our algorithm we are apply every operation in our list. Consider as a heap. So if you see the implementation, so we are not creating any tree or anything in our course. We are just applying every operation on our list, and we are considering this list as a heap. Okay, so heap. Now how we can create the heap? So some many questions are comes on this heap topics, and you have already seen some question from the previous term. Okay, so for example, we have so there are two types of heap: max heap and min heap. Okay, so in max heap there is one condition: parent nodes will always greater or equal to their child's node. In min heap, parents node will always less than or equal to their child's node. Okay, so this is the one rule for the heap if we are creating a max heap or min heap. So for example, if we have a sequence 10, 20, 1, 7, 3, and 5. Okay, so we are this sequence is given, and we want to create a max heap. Okay, so we will add element one by one in our. Okay, so this is given a sequence, so and we are creating a max heap. So basically we will for this heap. Okay, 1 second. Yeah. So okay, for example, we are considering that. So first, how we can create the max heap? So first, we will add 10. Okay, so single node we can say that this is a heap. Okay, this is a max heap. Okay, we are just creating a max heap. If we are adding the 20 in our this heap, okay, so 10. Now we will add the node in our complete binary tree fashion. Okay, so the 20 will come at the left position. Okay, so 20 we will add here. After adding this, we will just check that who is the greatest on this parent of child value. So now 20 is greater than then who is the largest? So there is one algorithm, heapy, max heapy, some algorithms are given. So basically how the algorithms can perform this operation basically. So we just consider that this is the largest. Now we will just compare the element 10 or 20, who is the largest. Now 20 is the largest. Now we will swapping this value, largest and the parent value. So after this we will get this 20 and 10. Now it become a max heap. Okay, for this part 20. Now we will add 1. Okay, so now 1 will be add into right side of the 20, 10 and this 20 1. Okay, so we will repeat, we will check again this information, the who is the largest. So we are just starting from the parent node. We are just consider that this is the largest, the parent is the largest, and now we will compare the this parent value by their child value. Okay, so now 20 is largest. Now we will check, compare this by 10. So after comparing this, 20 is remain the largest. Now we will check with the right child. So 20 and 1, the 20 is the largest. So the parent is parent in the final process. After completion of this process, finding the largest value in parent on both child. Okay, so if the parent, the largest position is not changed, so we will remain the same. So now this is a max heap. Now we will add 7 in this previous max heap. Okay, so 7 will add here, 10, 1, and 7 will add here. Okay, because we are adding the element in the complete binary tree fashion. So 10. Now we will check the parent, who is the parent of this 7 is 10. Okay, we will check the who is the largest of this part. This is 10, so there is no change. We will stop. We can see that this is the max heap. We'll just add 3. So 3 will add here, 20, 10, and 1, and 7. Now 3. Same things. Now who is the parent of this 3 is 10, and who is the largest in all 3? 10. So there is no change. So now we can say that this is the max heap. Now we will just again we add the 5 value. So 5 value will be add 20, 10, 1, 7, 3, and this is 1. So this is 5. Now who is the parent of 5? 1, and we will check that who is the maximum of this part, 5. Okay, so if value are swapping, so maximum is the largest of this part is 5. So in this process now it become like this, 10, 1, 7, 3, and this is become 5, this is 1. So if value are swapping, then we will check the parent node again from here. Okay, so we will check the parent node. Now we will check, because value is updated now, so the child value of this 20 is updated from the lower side. So now we will check the this CPY process on that part all once again. Okay, so now we will check who is the largest among these 3 elements. So this is the 20, so there is no change. So now it will remain as a 20, 10, 5, and 7, 3 as 1. Okay, so this is the final maxi for the given sequence. Okay, so for example, if
Sir,
we are
what
adding,
if there is one more 20 at the end, sir? If there are two same numbers.
okay, for example, if we are adding 20 now. Okay, okay, fine. So we are just adding this like 20, 10, 5, and 7, 3, and 1, and 20 will add here. Okay, so we will check who is the parent of this 20 is. So now this is the parent information. So we will check that who is the largest of all these 3 nodes. So now 20 is greater than this 5. Okay, so we will swap this node once again. Okay, so now it become a 20, 10, 5, or we will just compare when we add the element, new element, we will just we can just compare by only parent node. So there is no need to compare by this left or right child also. Okay, so we can compare that this only this part. If the newly added element value is greater than the parent, then we can directly swap. Okay, so 10 7, now this is 3, now this is 1, and so this is it become a 20 and it become a 5. Okay, now because the child value of 20 is updated, now we will check again. We will compare this value from this node. So largest, now this is 20, now this is 20. So we can say that the largest is remain the parent node. So there is no update will happen. Now this is the maximum.
Sir, so this is the tree that will be finalized. This is the final tree.
Yeah, this is the final max heap actually.
Final heap.
Yeah, final max heap. We are creating a max heap.
But in one of the quiz question, but in one of the
so okay, I'm taking that question.
same where two search tree, it was a quiz, it was a balanced search tree.
1 second. Yeah, your voice is not clear to me. Is it for everyone?
Yes, sir. His voice is breaking.
Yeah, so your voice is not clear. Actually, it's breaking a lot.
Sir, there was a question in quiz. They have given the options that
Anushka, your voice is also now not audible to me. Hello?
Hello, sir.
Can you
Am I
repeat
audible,
your
sir?
voice?
Siddhant.
Siddha. Yeah, Siddhant. Hello?
Yeah, sir. So last year quiz, there was this similar question in a balanced search tree.
Okay.
So both the same numbers were there. There were two same numbers. So both the numbers got eliminated in the final balanced search tree, sir.
Balance search tree, or you are talking about heap or balance search tree? This is actually heap.
I'm talking about balanced search tree, sir.
So this the in binary search tree actually
Okay.
we just ignore the duplication of the value. Okay, so in binary search tree we not store the duplicate value in our search tree. Okay, so yeah, there is one question
Okay,
related to this heap actually. So what are the question? Okay, I'm just representing here. For example, one max heap is given. Okay, so you have already seen the adding process, how we are adding the new element, and during the adding process. Okay, so for example, if we are just added one more node. Okay, this is 25. Okay, we are adding the 25 in our max heap. Okay, so after this adding 25, what will be where it will add now? So 20, 10. This is now 20. This is 7. This is 3. All levels are filled. So 5. Now this 25 will add here. Okay. After that, we will just compare this 25 value by their parent node. Okay, so if 25 is greater than this parent value 7, yes, it is greater. So now we will swap the value. Okay, so this 25 come here and this 7 come below. Okay, now it become a 25 come here and 7 come here. Okay, now once again we check the this 25 is greater or less than this parent value. So 25 is greater than this 10. So this element okay, so this 25 will swap by this 10. Okay, so this 25 will move up, so it become a 25 and it become a 10. Okay. Now we will just check that 25 is greater than this 20. Yes. So we will just swap this value. Okay. So now it come 20 here and it come 25 here. So if you can see this fashion to add moving the element in our heap. So if we are adding from the leaf node, and this if value is greater than, then it is moving from the leaf node to the parent node by this path. Okay, so by this path. Okay, so this 25 value cannot come on the other child in other child. For example, this 25 cannot come in this 3 part, or cannot come this in this part. It can move only there is only one path from this last added node place to root node. This is the path where it can move into the upside. Okay, so same problem is given in which, so where the one max heap is given. So for example, I'm creating one max heap is given. Okay, so maxi, for example, 30. Okay, so this is 25. This is for example, this is less than 1 over 16. This is 20. This is 22. This is 23. Sorry, 20. No. This is 12. This is 15. This way, okay. So this is 18. This is 9. Okay, now we are in the quiz. There is a question: who is the last inserted node in our max heap? Who are the possible last inserted node?
No, no, sir. The question was that which node we can't insert at the last.
Okay, okay, yeah. So just repeat it for reverse question. Okay.
Uh-huh.
So who cannot be the last inserted node? That is the question. Okay.
Yes.
So so last inserted node happened from this position. Okay, because this is the last position.
Yes, sir.
When we inserted any node in the last, so it first we will add at this position. Now this if the value is greater than, then it moves up to the parent, like in the previous example where we add the 25 and it moved to the parent node. So you can return the answer, just see why. So there is one just option is given like that is 30, 20, 25 and 22. Okay, last 16. So last inserted node, if the value is greater than, then it can be moved in that way only. Okay, so for example, 20 is the last 20 is the last node. So 20 is the last inserted node. Yeah, so before that 20 is the last node. Yeah, so before for example 20 is the last inserted node, so before that the binary heap will look like that: 30, 25 and 16, and this value is the 18 and this is the 9. Okay, so no 20, no, this is not possible. Yeah, correct. So 20 is also not possible. 1 second.
Sir, actually, let me reiterate the question again. The question was given that we were provided a max heap, okay, and we have to insert each element which were given in the option, and we have to cross check which element can't be inserted at the end. Means we have ended at 9. Here in the max heap, we have ended at 9th node, okay. So if we insert 30, we will insert it at 22. 30 will be the leaf of 22, and then we will check one by one.
No. So actually, we are talking about this 16. Actually, it cannot be the answer because 16 at this place. Okay. So last node inserted at from this position. So it can move only this path.
No, sir, that is not the question. The question was like if you rebuild the heap again and insert 16 at last position, then will we be get the same heap?
So I would just wait. I'm just checking the what are the exact question is.
Share the question now.
Second. Wait. Yeah.
So I guess it was something like we cannot share the same number which is already present in the heap.
No, so this is the one quiz of the previous term. So can you tell me?
14th number. 14th.
So the sequence is the different actually.
Sir, okay.
So just check the question.
Yeah, scroll down.
There is one question related to min heap.
Sir, wait. Yes, this is the question. Yes.
Okay. Consider the min heap. Okay, this is the min heap built by repeatedly inserted value into a which of the following could not have been the last element. So same things. We will just create the min heap for that. 1 second.
Here the question says it could not be inserted, sir. So anything in the middle, not in the path.
Yes.
We
So
have
first
to-
we have to create the min heap for that. So min heap is, so this is the min heap actually given. Okay. So 10, now 25 and 45 and 35 and 38 and 70, 54, 43 and 39. Okay, 39. So this is the actual min heap which I have already given in the problem statement, and the last inserted element happened from this position. Okay, so we will just check that who are the elements come in that path. Okay, that these elements are the possible elements which inserted at the last position. So 25 is in the given path, 35 is also given in that path, 39, yes, it is the last, 38. So 38 is not coming in that path. Okay, 30 is not in that path. So after adding after adding an element, so it can move to up only by the swapping on the parent nodes, not the siblings nodes. Okay, so if we are adding this at the last position 39, so we can move up, we can swap the value by their parents nodes only. Okay, so last inserted node, for example, we are adding 10, so 10 will move, compare this parent node, then again we compare the parent node, then we again compare the parent node. We will never compare the value by the siblings, so we are never compare from this position to this position and never swap this position. Okay, so 38 cannot be the last inserted element, because if we are adding 38 from here, so it can move only the path to the root node. It cannot come into the another path. Because of that, 38 cannot be the answer for that node.
Thank you so much, sir. Thank you so much, sir. Sir, you told the easiest way to calculate that. We thought this is a very
No, this is a very easy way. Actually, the
From the
question
answer,
are
we
based on the
concluded
logic.
about it being the midpoint, but it is something very different from that.
No. So, okay. So I saw that one person yesterday discussed with the prejudice. So, okay, so just move to the topics.
In the same question paper,
Sir,
sir.
please explain this one.
Which one?
Sir, one more question, sir. We next smaller, next larger. How come both
Okay.
takes?
Okay. Okay, next smaller and next larger. So in heap, actually, okay, just I'm explaining that question. So
Once again, sir.
so for example, we have a max heap. Okay, so
This question once again, sir, please.
which question?
Sir, that 38 one, previous one, sir.
38 one. Okay. Oh, same one which we are discussing. No.
Yes, sir.
This one.
Yes, sir. Insert one.
Yeah. So what is your query?
How did you do it, sir? This one once again, can you
Oh,
please
okay. You are
explain?
just telling, asking again. Okay. So if you see the previous explanation, when we are creating the heap. So if anytime we are getting, so in this example, we are just adding one by one node in our heap. So if anytime when we are adding the new nodes, so nodes can be traversed from the adding position to the parent position only. Okay, so for you, if you see the last addition information, where is this 25? Yeah. So for example, now I'm creating 1 second. 20. This is the max heap actually 10, 20, 7, 3, 1, 5. Okay, I'm just adding the 25 value in this max heap. This is the max heap. Okay, I'm adding this 25 value. So 25 value will be add first here. Okay, and this 25 value can be moved only to their by swapping their parent node information. So we will just compare this 25 to their parent node to maintain the max heap property. We will just compare this 25 by their parent value. So 25 value is the greater than the 7 value. So this is the violating of the max heap. So we will swap this value. Now 25 at come here and 7 come here. Now this 25 we will compare by their parent node. So this is greater than this 10. So this value will come here and this come here. Now it become a 10 and this 25. Okay, now we will compare this 25 by 20. So this is greater than this parent information. So it become a 25 and it become a 20. Okay, so you can see that we are just comparing the added value by their parent value. Okay, we are not comparing the added value by their siblings value. So we are not comparing this 25 by 3, and we are not performing the swapping operation with their siblings nodes. Okay, so any new added node can be moved up to their parent root node by their swapping of their parent nodes. Okay, so in the last adding position, just see the path, who elements are coming in that path. So for that question, which we are just explaining that, yeah, for this question, you can, so this is the min heap actually given. Okay, so after that you will create the min heap first. Okay, then check that. So last inserted node position is this, and if the value of this node is inserted node is the greater than their parent node, so the value can move only this way by their parent node information. Okay, so 39 to parent, who's the parent of 39 is 35, and who's the parent of this node is this one, who's the parent of this node is this one. So we will these are the possible node which are inserted in the last. So we are not swapping any time by their siblings value. So in given option 25 coming in that path, yes, it can be possible at the last inserted node. 35, 39 all are coming in that path, but 38 is not coming in that path. Okay, so this 38 cannot be the last inserted node, because if you are adding 38 from here, so it cannot come at this position after inserting this. It can come on this path, but cannot come on the other path. So because of that, this 38 cannot be the last inserted element, because last inserted element always move to the path which is connected to the root node. Okay, clear?
Sir, I have a question from quiz 3.
Who is
It's Huffman coding.
okay? We are just coming in the B7, then you can ask. Okay.
Okay.
First, we are just finishing this. So this is the min heap and max heap concept. So we can create the min heap and max heap in that way. So we are also used this max heap and min heap concept to sorting our elements. Okay, so how we can sort these elements using max heap or max heap or min heap concept. So we can just sort, for example. So for example, if we have an input list, this is the like this 10, 1, 3, 8, 2, 5. Okay, this is the input list for we are interested to sort this list using the heapify process. So first we will create the max heap for that input. So max heap will look like that. So 10, first we will create 10. Now 10, 1 come at here. So now this is the max heap. Now next position 1, this is 3. Okay, this is max heap. Now 8. So 10, 1, 3, 8. Now 8 is greater than 1. So we will swap that. So it become a 10, 8, then 1, and then 3. Okay, now 2. So 10, 8, 3, now 1 and 2. Okay. So there is no violation. Okay, now 5. So 10, 8, 3, 1, 2, and 5. Okay, so this is the violation. Okay, now swap the value. So 10, 8, 5, 1, 2, and 3. Okay, so this is the max heap. We will create the first time max heap. After that, so what are the list representation for this max heap is? So first element is 10, 8, 5, 1, 2, 3. Okay, this is the list representation of this max heap. So this in max heap, the largest element at come on the first position. Okay, this come at the first position. So we will just swap the value of this 10 and this 3. Okay, so we will swap the position value of this first and last position and reduce the size of by 1. Okay, so by swapping this, what will be the list is 3, 8, 5, 1, and 2, and 10. Okay, after that we are reducing the size of max heap. Now the size of max heap is this, and we just created the max heap again. So this is the 3, 8, 5, 1, and 2. Okay, we are not considering this 10 into our max heap, and we will just heapify this max heap, because this is not a max heap now. So we will apply the heapify process. So we will apply the heapify process from this node. There is no child for that. Now we will apply from this 8. So in this part, this 8 is greater. Okay, there is no problem. Then now we will move to this 3. So for 3, now it move to the 8 here, and 3 here, and 5, and this is 1, and this is 2. Now if we child is changing, that we will just check again here from this combination, which is following the property of max heap or not. So 3 is greater than the child. Okay, now this is the once again we are creating the max heap for the remaining elements. Now this 8 come at the top position. So if we are just representing this as if once again as a list form. So now 8, 3, 5, 1, 2, and this is the previous element. We are not considering into the heap. So now this we will swap this position element last. Okay, now it can come here to 3, 5, 1 and 8. Okay, and reduce the size of our maxi by once again. Okay. So now once again 2, 3, 5, 1. Okay, now this is not a maxi. We will just check that there is no problem with this part. Now we will check on that parent nodes. Yes, who's the max is this 5. So we will convert into the max heap now 5, 3, 1, and this is 2. Okay, now this become a max heap once again. So now we just write this in that way. So 5, 3, 2, 1, and this is the part which not considered 10. So we will swap this part and become 1, 3, 2 and 5. Okay, and reduce the size of our list 8, 10. Now it is the next part 1, 3, 2. Okay, just check that this is the max heap, non-max heap. Okay, just create the max heap once again. Now it becomes 3 and become 1 and become 2. Okay, now come at 3, 1 and 2. Just swap this part and this will become a 2, 1, 3 and reduce the size now 5, 8 and 10. Okay, so now we are remaining that 2 and 1. Okay, so this is the max heap. We will repeat the same process again. So we just swap the last element. So this is the last 1 and 2 and reduce the size 3, 5, 8 and 10. Okay, now remaining one element. Once again, this is the same 2, 3, 5, 8 and 10. So this is the process to sort the element using the max heap concept. Okay, every time we create the max heap and we just swap the root node value to the last node, and every time after swapping we are reduce the size of heap by 1. So same our element are sorted into the reverse order direction. Largest element come at the last position, second largest element come at the second last position. So in that way our sorted list created. So we can use this concept in our heap sort. This is called the heap sort algorithm. Okay, now this is the improved digestive algorithm using min heap actually. So this is the some complicated algorithms which is explained in the lectures. This is the code based. Heap sort is given. Okay, yeah, binary search process. Now, so binary search is also a binary tree, but there is a rule. So what is the rule actually? The binary search tree is a binary tree that is either empty or satisfy the following condition. For each node v in the tree, the value of the left child or left subtree. Okay, so this is the rule actually. Value of the left child or left subtree is always less than the value of v. Okay, for each v, so this is the first condition is given for the tree. For each node v, so we will apply this we will check this condition for every node of the tree. So the value of the left child or left subtree is always less than or the value of v, and the value of the right child or right subtree is always greater than the value of v. Okay, so this two conditions should be satisfied for the binary search. So if we can represent these things, how we can create the binary search tree, how we insert the binary search tree. So for example, if we have a given sequence, so this is also a type of persons. So for example, so we have 8, 1, 3, 9, 4, 6, 10. Okay, we have a given sequence and we are asking that create the binary search tree for that. So we will just start from the first node for the given sequence and just create the binary search tree. And every time we will start from the root node for the insertion of the node. Okay, so just we start from the 8. There is no node in the tree. Just add that. This is the binary search tree for the 8. Now we add the 1 value in our given binary search tree. So we will start comparison from the root node always. Okay, so 1 is less than the 8. If the value is less than the node value, just move to the left side. Okay, if the value of the greater than the current node value, just move to the right side and move until you find the empty place for the addition of the elements. So 1, so 1 is less than 8, so there is no node is available for the left side. So this is the empty place to add this one. Just add that 1. Now next element is 3. Okay, so 3 is less than this 8. Okay, so move to the left side. So your node is available. Yes, just compare again. So 3 is greater than this one. Yes, so we will move to the right side. So there is no node is available on the right side. That means the empty place is available. So you can add 3 here. Okay, same for the 9. So 9 is greater than 8. So just move to the right side. So empty place is available. Just add this here. Okay. 4 is less than 8. Move to the left. Node is available. Greater than 1. Yes. So move to the right. Node is available. Let's compare again. So 4 is greater than this 3. Yes. So now empty place is available. Add this 4. 6 less than 8. Greater than 1. Greater than 3. Greater than 4. Now empty place is available 6. Now 10. So greater than 8. Greater than 9. And empty place is available. Add that. So this is the binary search tree creation way. Okay, so we just added node one by one. Don't create the binary search randomly. Just choose the node, any node from the given sequence, and create the just apply the rule, binary search rule randomly. That we create the problem. Okay, just add node one by one and follow the insertion rule. Every time start from the comparison from the root node and add the node at the available position, empty position. Okay, so this is the binary search tree. So this is the insertion way. So a binary search tree, if this is not balanced, so the sometimes in the worst case situation, it gives the big one complexity to finding the element or insertion of the elements. We can say that. So there is no benefits for unbalanced binary search tree actually. Okay, if the search tree is balanced, properly balanced, and the height of the balanced search tree is log n, then we can use the benefits for the binary search tree. Okay, so in that if the binary search tree is balanced, so we can find out any element of the our binary search tree in the log n times. We can also insert any element in log n times. Also, we can delete any element in log n time if our tree is balanced. So for example, if sequence is given like that 1 2 3 4 5 6 7 8 in that way, so our tree will be look like that 1 2 3 4 5 6 7 8. So there is no benefit. This is similar to like our list. Okay, so we will start from here, and every time we have to compare the each element to reach at the last position. Okay, so the height of this tree is actually the equal to the number of elements. Total number of elements is 8. The height of this is 8. So our binary search tree like created using like this way. For example, 5. This is 4. This is 3, and this is 4. This is 2. For that like that. So this is 7. This is 6. This is 8. So total elements are 7 here. Okay, but the height of this tree is 2 only. So you can reach at any element. So height is 3. Okay, so 1, if we are considering that the height of the root node is 1, 2, and 3. So this is the height of our tree. So you can find any element using in 3 comparison. Okay, so this is the binary search tree. So this is the insertion way. Same for the deletion. So we can delete and any node from the given binary search tree. So for example, if we are creating a node, if we are deleting a node which have 0 child, so we can directly delete it. For example, if we want to delete this 8 value from our binary search tree, so we can directly delete it by just save the information of the parent node as in none. Okay, just save the none information of the left child, right child field. See, it will be deleted in the single operation. So if any node which have the one child, okay, so for example, if we have a tree like in that way, and we are deleting this 7 node from here, so it has a one child, and just change the value, just change the value of the child node field, and 6 will come here. Okay. And this becomes 7, and just remove that part. Okay, so after removing this, it remains same. And for example, if you are removing the node which have both child, so for example this things, okay, so if you are removing this 8, so you have to replace this node information by the maybe in order successor or in order predecessor. So if the who is the in order successor now? 9. Okay, just swap the value by this node, so it become 9, it become 8. Now check that what are the condition for that node for remove. Now there is only one child. Okay, so just save the or you can directly save the child information from here. Okay, so in the right child field, if is there any another child is available, for example 12 is available, just store the this child address in this right child field. Okay, so after removing this address, this 10 will be removed. So in that way, we can remove the any node from the binary search tree. So this is the last topic for week 6, binary search tree, and we are moving to the next. Is there any question from the week 6? Big 7. Okay. So we have already seen the what is the binary search tree actually, or there's no advantage if the binary search tree is not balanced. So for balancing the binary search tree, we use this algorithm AVL tree. Okay, so AVL tree is a algorithm that just create the balanced binary search tree. So there is some rules for create the AVL tree actually. So these are some property. Balanced tree have height, log, and using rotation we can maintain. So there are some rotation methods. So using this rotation method, we are just created a balanced binary tree. Height balanced tree have height, this log, and find insert these operation can be possible for the balanced tree in the log n times. These are the formula to find out the minimum number of nodes in AVL tree, or we can say the balanced tree created by the AVL. And this is the maximum number of nodes. This is similar to the our binary tree, complete binary tree formula. Okay, so maximum nodes if all labels are filled like a complete binary tree. So how we can create the AVL tree and how it rotates the tree to maintain the balance. So we can understand this. So there are different types of rotation actually, and for when we are applying which rotation, it depends on the balance factor value. Or sometimes we say that slope value. So we are considering that what are the height. So for example, if we have a tree, so three. First thing, how we can find out the high balance factor for each node. So for example, this is the tree A, B, C, okay, D, that way, okay, and E and F. Okay, so for height, we update this height information from the leaf nodes. So we just consider that the leaf node have the height, or we consider the depth, or you can use anything. So what are the height for this subtree? This is the one. If we consider that what are the height of the E is, so the maximum length of the any maximum length of the path from this E to any leaf node which is connected from this E. Okay, so there is only one path connected to this F. So this is the what is the length of this is. So the height of this is 1. Now we will add the 1 into the longest path. Okay, so this is the 1. Now it will commit 2. Now there is no, this is the leaf, this is 1, this is, there is a leaf, this is 1. Now for B, so who is the longest? So we will just check the child height value. So which is the largest, because we are updating this height from the leaf. So there is no check to the complete path. Just check the height of the child nodes, which is the maximum. So this is E height is the maximum 2. Then we will add the height here. 2 plus 1 is 3. Okay, now for A, so who is the maximum? 3 and 1, 3, 3 plus 1 is 4. So this is the height updation. Okay, and now we will calculate the slope value now. So for checking that our tree is balanced or not, we calculate this slope, or sometimes called the balance factor. So how we can create this balance factor? So there is no, we will create the balance factor for every node. Okay, so we can create that there is no child for that this F. So the height of this child node is 0, and so left height of this child node is 0, and right height of this child node is 0. So 0 minus 0. So for this slope value, slope value, we just created the left height minus right height. Left child height and minus right child height. And what are the mod value here? So this value should not be greater than 1 for the balance tree. Okay, so what is the slope value for F is? So 0 minus 0 is 0. Okay, so now I'm presenting this 0 here on the right side of the on every node. Okay, so what is the balance factor for E? So what is the height of the left child is 1. Okay, what is the height of the right child? There is no right child, so we are considering that 0. So 1 minus 0 is 1. Okay, so for this node, so there is 0 minus 0 is 0 node. Just change it. 1, and this is 0. So this 0 minus 0 is 0, and this for B. So what is the left height is 1, and right height is 2. So 1 minus 2 is minus 1. So you just take the positive value, which is 1. And for C, so 0 minus 0 is 0, and for A, what is the? So this is, yeah, this is 3, and 3 minus 1 is 2. Okay. So at the time of creation of binary search tree, so in binary search tree we always add one element at a time. So after adding element in our binary search tree, we will just check that every node balance, the slope value should be less than this 2. Should be less than 2. Okay, if it is greater than 1, then that means our search tree, binary search tree is unbalanced. So we have to apply some rotation to make balance binary search tree. So okay, this is the way to how we can create the balance slope value for every node. How we can find out the height of every node. Okay, so this slope value should always be greater than 1. Okay, if the slope value is 0 and 1, so there is no problem. We will consider that our tree is balanced. If value is 2 or 3, so that means our tree is not balanced. So we have to apply the rotations. So for example, so there are some different type of rotations. So for example, if we are creating 1, 2, 3. Okay, so this is the sequence actually we are inserting for the tree. So we will insert first 1, then 1 after. So we will create the balance factor for that. So this is 0 minus 0 is 0. There is no problem about it with this tree. Now after adding 2, so what is the balance factor for every node is? So this is 0. This is 0 minus 1. Okay, so the height of this 2 is actually 1. So 0 minus 1 is 1. So balance factor for this is 1. Okay, so same for there is no problem with this. Now 3, 1, 2, and 3. Okay, now the balance factor for this is 0. This is 0 minus 1. So this is 1, and this is 0 minus the height of this 2 is 2. 0 minus 2 is 2. Okay, now the this balance factor value become 2 more than 1. Okay, so now we will consider that now our tree is not valid. So we have to apply the rotation from here. So at any time, if any node balance factor value become 2 or more than 2, so we will check that from the last inserted node position. So this is the last inserted node, and who is the first node which have this balance factor greater than 1. So this is the first node from this last inserted node position. So we will apply the rotation. So there are 3 type of actually 4 type of rotation. So we will apply the anti-clockwise rotation, we can say that, on this, apply this one node. So this is the point actually, and we will create the left child. Okay, so 1 come at the left position, this 2 come at this 1 position, so it become look like that. Okay, so this is the point, and just move this, just rotate this part in the anti-clockwise fashion. Okay, this 2 move up, this 1 move on the left side, and this 3 move on position up. So now this it become a balance tree. So now if you check the balance factor, so the balance factor will be for this is 0, 0, and 1 minus 1 is 0. Okay, so now it will become a balance factor. Same for this is the first type of rotation. So this for example the second type of rotation, if for example if we are inserting 3, 2, 1 in that way, so 3 we will add first. Okay, so the balance factor is 0, no problem. 3, and now 3, now 2 come at this position, so this is 0, this is 1. Oh sorry, this is 0 and this is 1 balance factor. There is no problem. Now 3, this 2, this is 1, 0, 1, 2. Okay, so this is now created an unbalanced tree. So we'll apply the clockwise rotation at this stage. So 2 come at this position, 3 and 1. So after applying this rotation, it becomes a balance 0, 0, 0. Okay, so this is the second type situation. Yeah, so I'm coming on that of every type of situation actually. So now there is a situation, the third type of rotation. For example, if we add 1, 3, and 2. Okay, so in this case, so if we create the tree, for example 1, this is the balance factor 0, no problem. This is 1, then 3. Okay, so this is 0, this is 1, no problem. And now 1 is 3 and this 2. Okay, this is the way to insert the element in the binary search tree. Okay, so if we are adding 2, 2 is greater than 1, less than 3, it come here. So 0, 1, and 2. In that case, okay, so last inserted node at so last inserted node is 2. Okay, and this is the left child actually. Okay, so this is the left child of our parent node, and the parent node is the right child of our their parent node. So this is called RL. Okay, in the previous example, if you see that, so this is the RR position. So this is the, we say that RR rotation, right rotation. If this is the situation, this is called the RR rotation. If this is the situation, this is called the LL rotation. And this is the third type of situation. this is called the RL situation. Okay, RL rotations. In that case, we apply two rotation on that part. First rotation we will apply on the child node. So this is the node which have the valence vector 2. So we will apply the rotation on their child node first. Okay, this rotation will be clockwise rotation at this position. So after this first rotation, it become 1, 2, and 3, and again we will apply second rotation on their node which have the two valence vector. So now this time rotation will be happen on anti-clockwise rotation. So 2, 1, and 3. Okay, so after two rotation, it become a balanced. So now 0, 0, 0, all have 0. Okay, so this is the third type of rotation. For example, if we have 3, 1, and 2. Okay, this is another case. So 3, there is no issue. 0, 3, 1, there is no issue. 0, 1. Okay, and 3, 1, and 2. So this is 0, this is 1, this is 2. Okay, so this is the condition LR. LR type of rotation. So first rotation we will apply on that. This will be the anti-clockwise rotation. So 3, 2, and 1. And second rotation we will apply on this 3. This is which have the two valence vectors. This will be the clockwise rotation. So now 2, 3, and 1. Okay, now it become a balance. So these four type of the rotation we will apply when we create the balance search using AVL algorithm. So for example, if we have any sequence, so we are taking just a 1, 3, 4, another sequence. Okay, so we have a sequence 1, 8, 2, 3, and 9, 6. Okay, and one more 4. So we have a given sequence and we want to create this AVL tree for this given sequence. So okay, so start from the first node. So this is 1 and the valence vector is 0. Okay, no issue. 1 and 8. Valence vector is 0, it is 1, no issue. Now we will just add 1, 8, and so 2 is greater than 1. Yes, less than 8. Okay, so 2 come at here. Now this is 0, this is 1, this is 2. Okay, so this is which type of this condition is RL. Okay, so R, this is the right child, this is the left child. So we will apply two rotation on that part. So first rotation, after first rotation, this will be like that way, clockwise fashion. So 1 and 2 and 8, and we will apply one rotation here. So 2, 1, and 8. Okay, so after two rotation, it become a balance. So now we have completed till now. So now we will add this 3 in the our balance part. So 3. So 3 is greater than 2, and this is less than. Okay, so 3 come here. Now, so after adding this, okay, so 3 balance vector will be 0. Just create the new part. So now we will add 2, 1, and 8, and this is 3. So this is the valence vector 0. This is 1. Okay, so this is 0. Now this is 1 and this is 2. So 1 minus 2 is this is 1. Okay. So height of this left is this is 1 actually, or this is the height of 2. So 1 minus 2 is minus 1. So we'll take positive value. So there's no issue with this 3 because the balance vector is under 2. So add one more. Now 9. So we will add 2, 1, and 8, 3, and 9. Okay, so 9 come here. It is also not create any problem. 0, 1, sorry, 0. Leave no. Now this is 2, this is 1. This is okay. There is no issue with this 3. Now add 6. So now 2, 1, 8, 9. So 6 is greater than 2, less than 8. greater than 3. 6 come here. Okay. So now 0, 0. So leaf always have a slope 0. Now it is 1. Okay. Now 2. So this is the height 2. This is 1. 2. This is also 1. Now this is left part is 1 and right part is 1, 2, 3. Okay. So 1, 2, 3. Yeah, this is the height. So 1, 2, 3. Yeah. So 1 minus 2 is 1 minus 3 is 2. This is come 2. Okay. Now it is unbalanced. So we will apply. We will check that which type of the rotation we will apply. Okay. So last inserted node is 6. Okay. And check that balance factor of the current node is 2 on this part. Okay. So check that which part have the highest weight. So right part is the highest weight. Okay, just this is the R position. Come at this child. Now check that the right child part, which have the which part have the last inserted node. Okay, so from here. Okay, so this is the left part, which is we added the last inserted node 6. Okay, this is the L position. So this is the RL type of situation. So we will apply 2 rotation. First rotation will be apply on that part. This will be the clockwise rotation, and second rotation we will apply after that. So first rotation we will apply on that 8 part. Okay, so 2, 1, and we will move in the clockwise fashion. So this 3 come at here, 3, and this 8 come here. This 9 come. So for maintaining the binary search property, this if this left part come at the root position, so the right child of that part will be added to this previous parent as a left child. This is come at here. So now adding in that way, the binary search tree property is not valid. So one more rotation we will apply on that part. This is in that way. Okay, so we'll move to this 3 will come at top. Now 2, now 1, and this is 8, this is 6, this is 9. Okay, so after 2 rotation, this is now 0, this is 0, this is 0, this is 0, this is 1, and this is 0. Okay, so all balance factor reduced to 0. Now we will add 4 here. So 3, 2, 8, 1, 6, and 9. So 4, and when will come for 4? So 3 greater than 3, less than 8, less than 6. Okay, so 4 come here. Okay. So we will check balance factor once again. So 0, 1, 0, 0, and this is 1. So this is 2 and minus 1. So here now it is 2 and is 3. So this is also. So now this is the final AVL tree, a balanced. We can say that the balanced tree created using the AVL method. So this is the way to create the AVL using these 4 type of rotation. If you have any query in the AVL part, you can ask. Okay, so after this AVL part comes at the greedy algorithms. So need to make a sequence of choice to achieve a global optimal. Okay, so actually we will make the choice on every local position, and after performing this local choice, we just get the final global optimum solution.
Excuse me, sir.
Yes.
Sir, one question was there in previous term quiz. It was asked that they have given number of nodes in AVL tree, and we have to find the minimum height of that.
A minimum height.
Huh.
Okay.
Yes, sir. Okay, sir.
So,
Number of nodes given was 35, and
okay.
we have to find the minimum height of that AVL tree, assuming that height of single node is 1.
Okay, so that means if root node is available, that height is 1. Okay. Hmm.
Yes, sir.
So we are just asking the minimum height actually. So that means for the minimum height, this is the maximum node. Okay. So for example, if we have a formula, if we are creating the maximum number of nodes with the minimum height. So for example, if we have a height 1, h equal to 1. So in binary tree, there is only one node possible. Okay. For h2, if we are taking h2, so you can just create in that way. So what will be the number of nodes is 3. Okay. For h3, the tree will look like in the complete fashion. So this is the maximum possibility of for that height 3. This is 7. Okay. So there is one formula you can create. So if the height is 2 to the power height is 1, h minus 1. So if the height is 1, okay, so 1 we cannot. So h minus 1. I don't know. Minus
Sir,
1.
this is for maximum number of nodes, na?
Yeah, so we are just asking the question in reverse way. We are asking the minimum height for possible for that node. So this is just the reverse of that question.
Okay, so means it is saying that maximum height.
Mm-hmm. So this is the actually we are creating the maximum number of nodes for h3. So if you are taking h4, so this it become a 15, h5 it become a 31, h6 it
Yes,
become a
sir.
60
63.
63. Okay, so
Yes,
31
sir.
it cannot be answered because the node total number of node is 35, so it is greater than, so we'll take the height 6. So this is the minimum height. Maximum can be more than.
Okay. Okay, sir.
Yeah. So greedy algorithm, basically we always select the optimum decision on the local, and we achieve the global optimum solution. At each stage, make the next choice based on the some local criteria. So never go back and revise an earlier decision. So we will never change the decision. Uh, Drastically reduce space to search for the solution. Greedy strategy needs a proof of optimality. Okay, so you can you have already seen some algorithm which are based on that greedy approach. So digestive algorithm frames Kruskal interval scheduling, minimize lateness of coding. So digestive frames Kruskal we have already seen in the previous weeks. So this works on this greedy approach. Actually, we always select the node with the minimum distance weight node in our algorithms. So that is the local decision. And finally, we get the shortest path for the overall problem. So in that way, this is the greedy approach. So after that, some problem are discussed, some different type of problem discussed in this week 7, which are follow the greedy approach. So there is one interval scheduling. So interval scheduling, some scenario is given. So IIT Madras special video classroom and different type of different teacher wants to book a classroom slots may overlap, so not all booking can be possible. Choose the maximum subset of maximum number of bookings which are possible. Okay, to so how we can solve this part? So these are the, is there any problem? Yeah, given. Yeah. So here some activities given actually, and in this given activity we want to perform maximum number of activity. So how we can perform this problem, how we can solve this problem using greedy approach. So our main aim is to perform maximum activity, and two activity cannot be performed if the time is overlap, the start time and finish time is overlap with others. So for this type of problem, so we can solve this using greedy approach. One second. This is the simple problem we have already, I think. So this is the A, B, C, D problem. First, we will sort these activity according to their finish time. Okay, so sort this activity. So so this is the first, which is the shortest finishing time. Okay, this is 2. So first is 1 to 2. Okay, I'm not mentioning the name of activity. I'm just finding out the how many maximum activity are possible. So next is 4. So we can choose any 3, 4, and 1, 4. And next is 5. Okay, so 4, 5. This is first start time. This is finish time for every activity. And next is 6. So 0 to 6. And next is 9. So 5 to 9. And 9 to 11. No, sorry, 8 to 10. And 9 to 11. Okay, so our first step is that we will sort the activity according to their finish time in increasing order. Okay, so this is the finish time, or we have sorted this activity. After that, we will select the activity from the first activity. So first activity will be selected because it is started from 1 to 2. There is no issue. Then we will select second activity if the next activity start time it is greater than to the last selected activity finish time. So if you see that this 3, this is the start time for the next activity, which is greater than the finish time of the last selected activity. So 3 is greater than, okay, so we will select this. Okay, now the finish time is 4. Now next activities where start time is 1. Okay, so this is less than to our last selected activity, so we cannot pick. Now we will check the next. So 4. So in the problem statement, I think confliction definition is given. So we can start activity. I think what is the check question? Yeah, 0 to finish at time. Then other activity cannot start before 4. It can be start at 4 or after. Okay, so we can start the activity if it start at the finish time. Okay, so the next activity, so last finish time is 4 and next activity is 4. So we can choose select this because the finish time and start time is equal. So we can select this. Now last finish time is 5 and next activities start time is 0. So we cannot select it. Same for the, so next is 5. So this is match the start time and finish time. We will select it. Now this is 9 finish and this is 8. Cannot select it. And this is 9. We can select it. So this is the total number of activity we can perform. So this is the total number of 5. Okay, so how we can solve this problem in that by the greedy approach. So this is the interval scheduling problem. So this is the algorithm. First sort the activity according to the finish time and then select the activity if the start time of the activity is greater than or equal to the last selected activity finish time. So it returns the answer. So same similar problem, minimize lateness. Okay, so this is also a similar problem where the algorithm is a little different. So here we sort all jobs. This is the algorithm actually given. Sort all jobs in ascending order of deadline. So in this problem, the 2 values are given. First value is the time taken. So this is the example. Okay, so for minimize lateness, so we have these activity 1, 3, 6, 2, 2, 9, 3, 1, 8, and 4, 4, 9, 5, 3, 14, and 6 to 15. This is the activity ID, and this is the total time which are taken by this activity, and this is the deadline. Okay, so we want to reduce the lateness, so minimize the lateness value. So we will first sort this activity according to this deadline time. So first we will sort. So yeah, so which is the smaller value? This is 6. Okay, so 1 3 6, and who's the next one is 318. 318. Who's the next is 229, 449, and 5 3 14, and 6 2 15. Okay, so after that, yes, okay, correct. So after that we will just check, we will select the time. So we will start from the 0, and if we will select the first, we will select the first activity, it takes 3 time. Now the ending time is 3, so 0. Okay, and the deadline for this is 6, and we are completing this before the deadline, so lateness will be 0 for that. So we will select the next activity. So not select, we will just apply the next activity. So this, it takes 1 time. Okay, so it will start from the 3 and it completed at the 4 time. It will take this. So this is the second activity. And what are the minimized lateness is? So deadline is 8 and we are completing it at 4 times. So it is also 0. So next we will add 2 and it completed at 6, and now 6 is less than 9, so it is also 0. Same for the next. So 6 plus 4 is 10, and the deadline for this is 9, so it become a lateness is 1 because the deadline is 9 and we are completing at 10. Okay, so now just added 3, so it become a 13, and deadline is 14, so we are just completing before the deadline, so it is 0. So 6 now added to one more, so 2, this is just 15, and we are deadline is 15, we are completing at 15, so it is also 0. So the maximum value of all these lateness, so this is the 1. This is the minimum actually, if we are performing in that. So maximum value of the all lateness of the activities should be the minimum in our scheduling. So this is the 1. This is the way to perform to reduce our maximum lateness value. So this is way to complete this minimized lateness problem. Now next is Huffman algorithms. So is there any question about the Huffman algorithm? Someone asking, what are the question actually? Hello? If someone asked the question about the Huffman algorithm, what are the exact questions?
Yes, sir.
Yeah,
So
so
the
what is,
question was, I calculated for the quiz 3 question and I got the answer as 11.35, but the answer given was 12, and it was note and given that the answer would be the nearest integer. So the nearest integer would be 11 because 11.35 I got as an answer.
so which is the question actually? Can you
So quiz 3, shall I share the link?
quiz 3?
Yes, sir.
Okay. I'll just wait, I'm opening that. This one?
Yes, sir.
Yes, sir.
Okay. What is the, how many bits will be used to encode this message? So where is, this information is given to give the most integer part?
So in my, it was given in my, it was the question paper.
I think no.
Let me share the link. Wait a sec.
Okay, send. So this value will always come in the positive, positive in integer.
Answer is positive, but it is not an integer.
No, so we are asking the how many number of bits is required. So bits is always come in the integer format. How you are getting the float
So
value?
please you solve this question.
Okay. So question, okay, I'm just solving this question. Okay, so just checking how we can solve this. Okay, so the question is given. So we have a 5 character and the probability is given for each character. Okay, so we will create a Hoffman tree for that. So what will be the Hoffman tree for that given? So we can consider this as a frequency for our characters, and we will create the Hoffman tree. So which one is the smallest two weight for the Hoffman this given
C and
frequency?
E.
Okay, so this 16 and this 11. Okay, so we will create the node. So this is the C actually, and this is the E. We can we can put in any order, left or right. So this is the value actually 0.16. Okay, so this is value is 0.11. Okay, just create this. So what will be the value is
27.
0.27.
C.
Okay, so there is no issue. So now we have selected this 16 part and this 11 part. Now check that which is the next two smallest value. So 20.22 you have, and 0.21 you have, and 30 you have, and the new value is 27. Okay. So which one is the smallest two? 22 and 21. A and B. A and B. So this is 0.22 and this is 0.21. Just create new part. So this is become 0.43. Okay. Now initially we have selected this part and this part. Now we have selected this part and this part. We are getting information. This is 0.27 and this is 0.43. Okay. Now we have 0.43, 0.27 and this 0.30 remaining. So this is the next two. So just consider this 0.30 here, D, and 0.30. Okay. 0.30, this is come at 0.57. Okay. So after adding this, we are getting 0.57. So now we are 0.43, 0.57. This is one. Okay. Now the Hoffman tree is created. Just create the codes for that. So 0, 1, 0, 1, 0. No, I'm sorry.
Sir, left is 0, then it should
Yeah,
be
yeah,
20.
yes, I am removing that. 0, 0, 1, 0, 1, and 1, 0, 1. Correct. So just check the code. B, C, D, E. What is the code for? Who is this? Prashant, can you mute yourself? So for A, and now what is the code for A is 10.
0, 0.
10.
Yes, yes.
Okay. What is the code for B is 11. What is the code for C is 0, 1, 0. What is the code for D is 0, 0. What is the code for E is 0, 1, 1.
11 0 1 1. Yes.
Okay, now we are asking that how many bits will be used to encode this A, B, C, D, E. Just add these all value. So this is the length. This is the length 2. This is length 2. This is 3. This is 2. This is 3. 2 to 6 and 6 12.
11, sir, 11.
No.
2
This
to
is
4, 4 plus 3, 7, 7 plus 2, 9. Okay, sir, 12. Yes, sir. Sorry.
okay. So how you are getting this decimal value?
So after this, I did the thing that A will take 2 bits, B will take 2 bits, C will take 3 bits, and so on. And we're then multiplying it with its probability, that is frequency.
No. So
And
actually,
then
the
we will
one
get
mess actually one
average.
message is given. One message ABCDE is given, and we are asking for the bits for this ABCDE also. Okay, you have the code for ABCDE. And okay, so you are just make the code for that this message. So what will be the code for this ABCD message is just add the all uh, code in the
All
sequence
the
with
bits.
1 0 1 1 0 1 0 0 and 0 1 1.
Okay.
Okay, so this is for E, this is for D, and this is for C, and this is for B, and this is for A.
So, but the
The
number
message
of bits
AB.
shall but the number of bits shall be multiplied by the average bits also, no? The frequency.
No, actually, this is message, and we have created the bit forms for this message. So you can count the bits. These are the represented as a bits 0 and 1.
Okay.
Okay, just count the length of for this message. This is 12. So probability, why are you multiplying this probability? Actually, the question is straightforward. We are asking that encode the message. Encode the message A, B, C, D, E. So this is the A, B, C, D, E is message given, and just encode this using this codes, Hoffman codes.
So,
Just
is there
you
any case in which we need to multiply?
no, in that question there is no case.
But is there a case? I'm asking about that.
No, so why are you multiply? Actually, yeah, there are. I think one
I
question.
studied this in lecture only.
Yeah, I think one question in your graded assignment is available where we are asking the length of the code for 1000 character.
So for length we have, okay, I got that.
Okay, so if we are asking that what are the length of the 1000 character, so just count the frequency
How
in
many times? Yes, how
yeah,
many times?
yes, then just multiply that. So this is the different question where the straightforward message is given. Just encode that using this point code. Okay.
Sir, question number 5 in this, in which inversion has been asked, that question also, could you please
Uh,
clarify that?
which question? In paper?
Yes, sir. Question number 5. Yes, this question number 5
This is
in an array.
so one
Yes, sir. Yes, sir.
This is based on formula.
Yeah. So I think if you see the this is the 8th actually. Okay, just I'm seeing that PD. One second. So this is the beak 8, and in beak 8, if you see that this topic counting inversion, so there is one formula given for that. Where is that? Yeah, this is the formula. So this is the formula where you can count the inversion, maximum number of inversions. So this is the possibility. You apply this formula and just got the answer.
Okay, sir. Okay, sir. The next question is question number 12. That is comprehension based. Sir, there a code is given.
1 second.
Sir, I first thought it is divide and conquer, but the answer is telling it is a greedy algorithm. Could you please make me understand how?
So in my question paper, I think this is a different
Sir, I
section.
shared the link. Use that link.
Okay, sir, you go down. I will tell which question.
This
Yes,
one?
sir, this question. Yes, yes.
Fine. So how you are saying that this is the divide and conquer? How where we are calling the problem? Where we are dividing the problem into a sub problems into parts or any parts?
Okay, sir. It is not a divide and conquer.
So divide and
So
conquer
how
problem
it is a,
statement that state that we will
we have
divide the
to
problem,
divide a
yeah,
problem into
into
sub
a sub
problems.
problems,
Yes,
yeah, then solve each problem separately and then combine the answer
yes,
again. Okay, so there is no
yes.
division process inside here.
Sir, why
So
is this not dynamic programming?
it is also not a dynamic programming because we are not storing the result, uh, same things. We are not solving the sub problems, and we are not using the result of the sub problem in calculate the final solution.
But sir, here we are doing recursion, no?
So recursion you can use anywhere. So the dynamic programming is a different concept where you did not use the recursion actually. Week 9 is not in
In the syllabus.
the syllabus. So see the I think the dynamic programming definition again. So where we just use the sub problem solution to calculate the solution for our final problem. Okay, so we start the solve sub problem first and store the result of the sub problem and then use this stored result to further solve the problem.
Okay.
Okay, so we will look this just revise this week 9 content once again then. So this is the actually greedy waste problem. Actually, what is the problem actually? So let coins be a list of k coin and most positive integer that are available in as much quantity as you want. You want to pay a sum of rupees X using as few coins as possible from the coin demonstration. Okay. Given in the list coins. Here the Python function pay coin X is calculated the minimum number of coins that can be used to pay the amount X. Okay. So for this code, so problem statement is given, code is also given. So we have a list of coin. Okay, so we have a value of coin also. So you can see the example in this format. So we have a list of coin 6157. Okay, so we can take any value of coin any number of times. So for example, to achieve this amount 17, so we can take 6 into 6 two times. Okay, so there is no limitation to choose any elements to only one time. You can choose any number of times. Okay, so how you can achieve this 17 value by minimum number of minimum number of coin selection. So for example, if you are getting the 17 value, if you select 7 two times, so you will get the 14 value. After that, you cannot select 5 because 14 plus 5 9 become 19. You cannot select 6, so it become a more than 17. So you have to select 3 coin for the 1. Okay, so total coin will be now 5, become a 5. And in another way, if you select 6 two times, 6 into 2 12, and select 5 one times. Okay, so the total number of coin is now 3. So this is the actual problem. So where we want to minimize the number of our coins to get this amount. Okay, so the problem is simply looking that so the algorithm, what is the algorithm is doing? It is sorted. So first it is sorted the coins. So same things we are applying the algorithm in the interval scheduling, minimize lateness things. So first we are sorting the coins list and we are selecting the largest coin first for the okay. We are selecting the largest coin first and we are dividing this coin by the value. How many times we can select this coin to achieve the value. So for given example, So for achieve 25, so select the largest coin value. This is 10. Okay, so after sorting, you will get this 10, 5, 2, 1. Okay, then you will select always the largest value first. So the 10 value you will select, then multiply by, so first 10 you select, now remaining amount is 25 minus 10 is 15. You can select again 10. Okay, so it become it now 20. Now remaining amount is 5. Then now 5 is less than 10, so you will select the next greatest value. This is 5. So after selecting this 5, you will achieve the same amount. So total number of coin is 3. So this algorithm return this value. Okay, so this while loop is selecting the coin in the shortest way manner after sorting the list. Okay, so because of that, this is the greedy type of algorithm, because we are first we are sorting the element and we are selecting the largest value. So this selection of the largest value is the local optimum decision. This is the local optimum decision, and we are using this local decision optimum. We are just finding out the global optimum. We are just trying to the getting global optimum solution, minimum number of coin. So because of that, this is the greedy type of algorithm. So in divide and conquer algorithm, so just see the code where we are just calling, where we are dividing the sub problem into sub problem, and we are just calling the part. We are just calling the function again on the left part or right part in that way. So that concept used in the divide and conquer approach. Okay, so yeah, so Huffman, I think I have explained the Huffman algorithm already. So in Huffman algorithm, just calculate the frequency of each character of the string, sort the character in increasing order, and select the two minimum nodes value and create the Huffman tree in bottom up manner. Okay, so this is the algorithm. So we have already seen so one example to how we can create the Huffman tree. After creating this Huffman tree, just assign the 0 value on left edge and 1 value on the right edge. So after assigning this 0 and 1 on our Huffman tree, you can find out the Huffman codes. There is one property in Huffman code is that the code all codes are the prefix code. Okay, so the properties are also given, I think. So all codes are the prefix code, means any codes which are so for example this. So if you see the code, one second. So if you see the code 10 sorry 1 0 1 1 0 1 0 0 0 0 1 1. Okay, if you see all the codes, so there is no code which are come at the as a prefix on another code. If you see this 1 0, this 1 0 is not a part of as a prefix of another code. Okay, so 1 0 is not coming at the as a prefix in other codes. Same for the 1 1. You can see that the 1 1 is not coming at the part of the prefix code of others. So this type of if all code have these property, that these codes are called prefix codes. So this is the property of the Huffman codes. Okay, now B8. Okay, so divide and conquer approach, break up the problem into disjoint sub-problems, combine these sub-problem solution efficiently. So first, this is the first step. First, divide the problem into sub-problems, and after solving the each sub-problem separately, just combine the solution efficiently. So you have already seen the some example of this merge sort, quick sort in the previous weeks. So these all are the example of the divide and conquer approach So these some types of new problems discussed in the lecture, counting inversion. So counting inversion definition is this. This is the definition of counting inversion. And inversion is a pair of ij, where the value of I is less than j, where j appears before I. If value of so for any pair of I and j. So for example, if we have a given any order, so any pair of I and j, if the value of I is less than j, so I should be come before j, but this is not happening in our list, so where j appears before I. So in this case, we can say that there is one inversion. So for example, so for example, if we have a list 1 3 2 5 4, okay, so after sorting, so this is the our given list. We will check all the pair of value. So we will check the, for example, this 1 and 3, okay. So 1 is less than 3 and 1 is come before this 3, so this is, there is no inversion for that. We will check this 1 and 2. So 1 is less than 2 and it come before this 2, there is no inversion. For same 1 for 5, there is no inversion because 1 is less than 5 and come before this 5. And same for the 4. So 1 is less than 4 and come before this 4. Now we will check for this 3, okay, for the next part. So 3 is greater than 2 but come before this 2, so there is one inversion. Okay, so there is one inversion. Just check the next 5. So 3 is less than 5, so there is no inversion. And next for this, okay, so there is no inversion. So 3 is less than 4. Just check this part here. So now 2 is less than 5, there is no inversion. 2 is less than 4, there is no inversion. Now for 5, so for 5 there is a inversion because 5 is greater than 4 but come before this 4, there is one. Okay, so there are 2 inversion is in our given list. So how we can find out this inversion using our given approach? Yeah, so in simply you can just create the this type of diagram. Just you can create a one sorted list and one is the given another unsorted list, and just match each element. After the time this crossing points return the value as a inversion, total number of inversion. So basically we are using this merge sort concept in our to find out this inversion count value. So in that case, so merge sort complexity is the n log n. So same complexity we can, if we are using this concept, merge sort concept, so we can achieve this counting of inversion in the n log n times. So these algorithms are given, you have already seen and solve the problems. Same for the closest pair. This is also a problem of the one divide and conquer approach, where we are just
Sir, and
first.
last, sir, after the recursive time complexity, why do we write ON thing? How can we know that? And what actually that ON is?
This is the time complexity for the process before before the dividing part of the algorithm. So for example, if you've seen that, so this is the one merge part, okay. So what is the complexity of this merge part actually? This is the complexity of n. Okay, so this is there is one loop is given, while loop, and so we consider there is a complexity of n here because we are calling this merge and count on the list after dividing. So if you combine this a and b, you will get the actual list after first calling. For example, we have a list
Time
L.
complexity is n over here,
For this,
or m plus n.
no. So here we are just calling this function from the a list. So a is the initial list. For example, this a have a.
Okay.
Okay. So this the length m plus n will become a the main n part, length of this A.
N.
So we can say that this is the time complexity for this merge and count is n. Okay, clear? And this is the part where we are just dividing the problem and merging the solution. Okay, so this is the first, we are calling into the first part. This is the second part, we are calling on the second part inversion count. After that we are just calling this merge and count algorithm. So this is the remaining complexity, so just leave this part. Okay, so what is the complexity of the remaining part of the algorithm? So the remaining part of the complexity is, highest complexity is this merge part. This is big O n. Okay, so because of that we are representing in that way. Every time in the this is the recurrence relation. So every time when we are dividing the problem into two sub problems, so this is represent 2t n by 2. Okay, so we are just dividing the first problem t into 2t, and the size of the each problem is n by 2. And after dividing this, there is another part of the program which takes big O n complexity. Okay, this is this part.
Okay, sir.
Okay, so this is the constant part, this is also a constant part, this is also a constant part. This is the main part which takes the order of n complexity. This is this one. Okay, so we represent the recurrence relation in that form. So t n, this is the first problem, we are applying the problem on n input. After that, in our problem we are dividing the problem into two sub problems 2t with the input n by 2 in each, and the remaining part of our algorithm takes the big O n time. This represent the recurrence relation. Okay, same for the quick sort. In quick sort, the partition part takes n times, and another part, we are dividing the algorithm into two parts, calling the again quick sort. So in that manner we can just represent the recurrence relation. Okay, so these are some example discussed in the based on the divide and conquer approach. So if you have seen already, so this is the counter inversion problem, closest pair point. It is also example of divide and conquer approach. So this is also one example, integer multiplication. So these are the all code based things. So how we are solving this algorithms, all are the quick select, fast select. So you have already seen the quick sort algorithms. The quick sort is the algorithm which select the kth largest or kth smallest element in the minimum number, so in the less times. So using the quick sort approach we can perform this quick select also, but in the worst case it takes the n squared times, which is also performed by the quick sort. So quick sort is also worst case time is O n square if the element are in the sorted order and we are selecting the first element as a pivot element. So same things for the quick select, it also takes the order of n square if element are in unsorted order. So there is one algorithm, MOM algorithm, where we divide our list into a block of list and select the median of every block, and after that we select the median of the median, all medians. So we can achieve we can find out the median value in order of n times, and using this median value which is calculated by this MOM algorithms, we can use this median as a pivot element in our quick select or quick sort algorithms. So this pivot element will always divide the input into two equal halves. So because of that, the height of the t become log n, and the solution complete solution times become n log n. Okay, so we can improve our time complexity for quick sort or quick select using this MOM algorithms. So these are some algorithm recursion tree. Yeah, so this is the recursion tree calculate the complexity in the creating the tree format. So some formula is given. I think this is the. So these are the examples. Just see the concept all are based on the divide and conquer approach. Okay, so now if you have any query, then you can ask.
Sir, week 8 graded assignment question number 4 and 5, if you can
Okay.
explain the details.
Week 8.
I didn't
Number 2 also.
understand the week 8. Okay.
Week 8 graded assignment.
Week 8 graded assignment.
Question number 2 and 3.
4 and 5.
2, 3, 4 answers.
Sir, 2 and 3 also.
This is actually formula based, which I have already discussed in the lecture. Actually, this formula. Okay, we will look at again. So 4 and 5. So which of the following option describe the recurrence relation that will give the above recurrence tree? If the cost to combine solution at each level is equal to 2n and the cost to compute the solution of subproblem at the leaf node is equal to n. Okay. So this is the diagram actually. So we are creating n into n by 3 and 2n by 3. So total become as a total number of steps becoming n.
So I want to know about 2n. How come we know that it is 2n and not n?
It is given in the tree diagram. So this is the tree already given in the problem statement. So we are dividing the problem into two subproblems. One have the n by 3 and one have the 2n by 3. After that, we are dividing this n by 3 into in that the same way. So for this type of creation, when we are created the problem into two subproblems, so always the complexity remain the log n actually. So what is the question actually? Which of the following options describe the recurrence relation? Okay, so recurrence relation. So you can just see that. So both are the different forms actually. Tn. So first part contains the n by 3 and second part contains the 2n by 3. So just check that. Tn, so Tn by 3 and second part contains T2n by 3. Okay, so in the problem statement is given if the cost to combine the solution at each level is equal. So you have already seen the merge sort algorithm in the, we have already discussed it this time before. So this is the solution, the cost of the combining the solution at each level, which is 2n actually. Okay, so in recurrence relation, we can directly we can represent the exact number of operation, or we can also represent the complexity of that part. Okay, so this 2n is represent the number of operations which is given in the problem statement. So after dividing problem into a sub problem, so there is a one part which actually combine the solution, which perform the combine the solution of at each level. So it takes 2n operation. Okay, so we can directly represent this 2n part with our recurrence part, and we can represent the complexity of this part. If any part takes 2n steps, so what will be the complexity of this is order of n. So we can represent also this complexity. But it can, so what is this? Yeah, Tn by 3 plus T2n by 3 plus n. Okay, so here the complexity is not given. Here the number of step is given. So number of step is actually 2n. Okay, so we cannot change the number of steps. Okay, we can represent the complexity at the place of number of steps. But if the number of step is given, so we cannot change the number of steps. 2n is the total number of steps to combine the solution at each level. But we are changing the number of steps. Okay, so this cannot be the correct answer. Here we are just saying that 3t by 3. So this recurrence relation represent that every time we are dividing the problem into 3 subproblems, and each had the size n by 3. So this is not the problem statement. Actually, you can clearly see that in the diagram. So here we are dividing the problem into 2 subproblems, and in this recurrence relation, this it represents that we are dividing the problem into 3. This first three is represent that we are dividing the problem into 3 parts each level. So it cannot be the answer. So these are 2 different forms to represent the recurrence relation, where you can write the exact number of steps, or you can write the complexity of that part. So this is the 2 correct for that. So if Fn is the upper bound for the above recurrence relations, what is the value of Fn? Yeah, so this is the log n or n log n. Yeah. So for this type of tree, so every steps, so at every step, total number of every level. So at every level, total number of step will be n. If you see the first level, total number of steps is n. Second level, so you have already seen that the combining solution 2n. So complexity of the first level at big O n, second level is also a big O n, third level is also a big O n. So the height of this tree will be approximately log n. So actually the base is different, but we consider as a is equal to the log n part. So here n to the power 3. So I think one formula is given in the year summary. So when you correctly, the input Fn is the time spent on the non-recursive work, R is the number of recursive calls. It's not. Yeah, so this is the line equal. Okay, so if we are dividing the problem with the equal size, actually, so every time we are dividing n by 3 and 2n by 3. If you are adding these 2 parts, n by 3 plus 2n by 3, it becomes n. So this formula will apply to calculate the complexity for that. So it becomes a log n height. Okay, if we are decreasing and increasing, so if we are increasing, if we are using the if we are increasing the size of our, okay, so every time we are dividing into a fixed number of subproblems. So every time we are dividing into a two subproblems. Okay, so in that case, the complexity become a log n always. But if the number of uh, series grows exponentially, each term is a constant factor larger than previous term. Okay, so in that case we use this formula. So I think this question is discussed the yeah. So in this way, there is one given. Yeah, if you see the problem number 2, consider the following strategy to solve a problem of input size and divide the problem into 6 subproblems, each of size n by 6. Number of steps required to combine these 6 solutions is 2n plus 3. We apply this strategy recursively till the subproblem cannot be further divided into subproblems. Okay. So here the actually so it is also a same things. So if we are dividing problem into a fixed number of subproblem at each time, so this the complexity will always remain the log n. The height is always remain the log n. Actually, this is given the formula in our notes or in the lectures. So in the problem number 2 and 3, and same for the 5 and 4 and 5. So in the 4 and 5, we are always dividing into two subproblems, and for the problem number 2 and 3, we are always dividing into a 6 subproblems. So if you are adding these things n by 6, 6 subproblem, each have the size n by 6. So complexity will be n log 6. So base is n log 6n. So we will consider as a simple log n, equivalent to the log n complexity. This is the upper bound actually. So we can use this upper bound as a log n. Same for the lower problem, where we are just dividing into two subproblem every time. So complexity of, because of that, the complexity is here. So this is the 3 by 2n. The base.
Sir, then in binary search we divide in two parts. So why is it only log n and not n log n?
So binary search. Oh, okay. So no, every time we actually ignore the one half part. We not process both the parts. In binary search, we divide the problem into two, not two problems. Actually, because of that, binary search is called the decrease and conquer, not the divide and conquer. In binary search, we always divide the actually divide the searching area and remove the half of the searching area every time.
Okay, sir.
Okay. So this is the different type of category. Actually, we use this term decrease and conquer. We are reducing the problem space. Okay, so there are some formula given on that base. If we are dividing the problem into subproblem in equal number of subproblem at every step, so you can use that directly complexity log n. If the subproblem size is created exponentially, so this is the format. So here we are dividing 4 every step. This is 4. So yeah, this is the second condition, increasing. If series grows exponentially, so then we will use this n log CR formula to calculate the complexity. So you can use this, you can learn this formula for this type of problem. There's only just two formula, equal and increasing. And what is the 3? So 3 is also similar. No, not similar. If we divide the problem into 4 subproblems of size n by 2, the number of steps required to combine the solution is 15 using some optimization. So combine the solution is the fixed value is given here 15. So this is the constant value actually given, and we are dividing the problem into 4 subproblem of size n by 2. If you are combine this n by 2 into 4 times, so it will not become equal to the n. Okay, so n by 2 plus n by 2 plus n by 2 plus n by 2. So it becomes 4n by 2. So that means size will become increased if we divide the problem 4 problem into subproblem. 4 problem size n by 2. By 2. Okay, so yeah, every time we are increasing the size of the problem here. If you check the second label, so its size will become a 2n. At the next level, it become a 2 to the power 2n actually. So if you are creating this, for example, 3 for that. So if you are starting from tn here, okay, so if you are dividing by t n by 2 and t n by 2 t n by 2 t n by 2. Okay, so total number of sum of the input is n by 2 plus n by 2 plus n by 2 plus n by 2. Okay, so it become a 4n by 2. Now become 2n. Okay, same case if you repeat once again. So 1 2 3 4. Now it become a 2n and 2n and 2n, and this is the 2n. Okay, so we are getting 2n from 4 and we are just repeating 4 times. So 2, it become a 8n size for at this level. So size is increasing in the exponential form. So here 2 to the power 2 to the power 1, here 2 to the power 3 now. Okay, so in that case, if the size of the each label is increasing exponentially, so we use this formula. We use this. This is the formula t n log c. The c value is the constant value is given r. So this become a solution for that. 50 not the c. What is c is actually 2. 40 n by 2. Okay, so this c value is represented by the how we are dividing these things. You can see here r equal to 4. So this value is represented as a r. C value is represented as 2, and t n equal to, we will apply this formula, then it become a n square. So use this formula. If the problem is size is increases or not, or remain the equal, so we can use two different type of formula. Okay, any other query?
No, sir, no other query. Thank you so much, sir, for solving all the problems, all the doubts we have.
Okay, welcome. Yeah. Okay. Okay, if you have no query, then closed. Sir, is there a session on this Saturday? No, there is no session for the Saturday. Ahmad, there is no session for this time. Okay, thank you all. Bye.
Thank you, sir.
Thank you, sir.
Okay. Yeah, all the best for the exam.